Gravity is the most familiar stranger in your life. You have felt it since the moment your body first pressed against the ground. Yet the truth beneath that simple sensation is more alien than anything your everyday experience prepares you for. It never announces itself, yet it shapes everything you will ever see, touch, or imagine. It keeps your feet connected to the earth, governs your heartbeat by holding blood close enough for your vessels to push against, shapes the oceans into tides, molds planets into spheres, forges stars from collapsing clouds, sculpts galaxies into spirals, and writes the large-scale structure of the cosmos itself. This constant force, or what you think is a force, has quietly choreographed the universe for 13.8 billion years. And yet, for all its familiarity, you do not truly know what it is. No one does, not fully. Not even with all the tools of modern physics, all the satellite measurements, all the laser interferometers, all the telescopes spanning continents. Gravity is the most universally felt and least universally understood phenomenon in the laws of nature. The strange part is that the misunderstanding begins at a very basic level. You may believe that gravity pulls downward because everything you drop falls in that direction. You may assume astronauts float because they're far away from Earth. You may imagine planets move around the sun because a force tugs on them. All of these ideas feel natural because they arise from instinct, but instinct is not designed to interpret the architecture of space-time. Your brain evolved to avoid predators, not to solve differential geometry. It thinks in straight lines, pushes, pulls, and simple cause and effect. Gravity does not. Gravity belongs to a world of curves and trajectories, a world where the passage of time itself depends on where you stand, a world in which the shortest path between 2 points is not a straight line, but a geodesic shaped by mass and energy. The true nature of gravity begins with a simple but profound realization. When you stand on the ground and feel your weight pressing into your feet, that sensation is not gravity pulling you down. It is the ground pushing up on you, preventing you from following the natural path you would otherwise take through space-time. Remove the ground and the sensation of weight vanishes instantly. You do not feel gravity during freefall because, in that moment, you are doing exactly what space-time wants you to do. Move along the straightest possible path in a curved geometry. Astronauts orbiting Earth float not because gravity disappears, but because they are in perpetual free fall, constantly falling around the planet while moving sideways fast enough to miss it. At the altitude of the International Space Station, Earth's gravity is still roughly 90% as strong as it is on the ground. The difference is that nothing prevents astronauts from falling. Weightlessness is simply the absence of resistance. Once you internalize this, gravity becomes more mysterious, not less. If gravity does not push or pull in the way your mind imagines, then what guides the fall of objects, the motion of planets, or the curve of starlight? The answer, discovered by Einstein, is that mass and energy tell space-time how to curve, and space-time tells matter how to move. A falling object is not being yanked downward by a force. It is following the natural geometry carved into space-time by Earth's mass. A planet does not orbit a star because something pulls it sideways. It follows a geodesic winding through curved space. Light itself bends around massive bodies, not because it has weight, but because space-time tells it which way to go. Gravity is geometry, not force. Understanding this transforms the universe from a stage onto which events unfold into an active participant, shaping those events. Yet even this elegant picture hides deep mysteries. We know from centuries of experiments that gravity affects everything with mass or energy. We know from the bending of starlight during eclipses, from the precession of Mercury's orbit, from atomic clock measurements, from GPS satellite corrections, from gravitational redshift, from pulsar timing, from gravitational lensing, and from direct detection of gravitational waves, that Einstein's description of gravity as space-time curvature works extraordinarily well. We know black holes exist, neutron stars collide, waves in space-time propagate at the speed of light, and that time passes differently depending on altitude. These results are not theories, they are measurements repeatedly confirmed by independent groups using different tools and different methods. They form the bedrock of modern physics. But for every question answered, gravity raises a dozen more. If Einstein's picture is so successful, why does it break down in the center of black holes or at the very beginning of the universe? Why can we describe the electromagnetic force, the weak force, and the strong force using quantum field theory, but gravity refuses to fit into that framework? Why is gravity so astonishingly weak? 39 orders of magnitude weaker than electromagnetism. Why does space-time expand? Why does the expansion accelerate? What exactly is dark energy? What is dark matter? Why does matter curve space-time in the first place? What is space-time made of? Is it continuous or discrete? Does gravity emerge from something deeper, or is it fundamental? These are not philosophical questions. They are the cutting edges of experimental physics, mathematical physics, and cosmology. Despite the uncertainties, physicists have developed hypotheses to fill the gaps. Some theorists propose that gravity might emerge from quantum information, similar to how temperature emerges from the motion of molecules. This idea aligns with the holographic principle, which suggests the information content of a region of space may be encoded on its boundary. Others argue that if gravity is a quantum force, it must have a particle associated with it, a graviton, a spin-2 boson, but no experiment has yet detected such a particle. Some attempt to quantize space-time itself, imagining it as a mesh of tiny loops or networks. Others propose that the early universe experienced inflation, a rapid expansion driven by vacuum energy, and that relic gravitational waves from that era may still echo faintly across the cosmos. These hypotheses are not confirmed. They are possibilities motivated by mathematics and by the drive to unify all known forces into a single coherent framework. The difference between confirmed physics and speculative physics matters, and throughout this narrative, that distinction will always remain clear. The misunderstandings surrounding gravity are not limited to deep theoretical ideas. Even widely shared interpretations of recent discoveries often contain errors. People say we photographed a black hole, but what we imaged was the dark region created by gravitational lensing of hot plasma swirling around the event horizon. People say LIGO heard black holes merging, but what it detected were distortions in spacetime that scientists later converted into sound for visualization. People say dark matter has been observed, yet what has been observed is only its gravitational imprint on galaxy rotation curves, galaxy clusters, gravitational lensing arcs, and cosmic structure formation, not the substance itself. People say Einstein's theory eliminates the need for Newton's, but Newton's framework remains extraordinarily useful for systems where relativistic effects are negligible. People say time is absolute because it feels absolute, but atomic clocks disagree even when separated by less than a meter in height. For a viewer to build real trust in the science of gravity, the truth must be presented honestly. What is proven must be presented as proven. What is theoretical must be acknowledged as theoretical. What is speculation must be labelled as speculation, and what is myth must be exposed as myth. The purpose of this script is not to simplify the universe into comforting explanations, but to guide you through its complexity with clarity, transparency, and depth. It will follow gravity from the everyday experience of falling to the curved geometry of spacetime, from Newton's revolutionary insight to Einstein's radical reimagining, from the bending of light to the formation of black holes, from gravitational waves rippling across the cosmos to the accelerating expansion of the universe, and finally to the unresolved questions at the boundary between relativity and quantum mechanics. Gravity is not just another topic in physics, It is the key to understanding why the universe looks the way it does. Without gravity, there would be no planets, no stars, no galaxies, no clustering of matter, no cosmic web of filaments stretching across billions of light years, no passage of time that varies depending on location, and no black holes hiding behind horizons where even light cannot escape. Gravity is the sculptor of structure, the architect of celestial motion, and the shaper of cosmic history. To understand gravity is to understand why the universe is not an empty, unstructured cloud of particles drifting aimlessly in the void. This journey will not be easy. Gravity defies intuition at every level. It demands that you abandon the idea of absolute time, absolute space, and absolute simultaneity. It requires that you accept that the shape of reality is not fixed but dynamic, bending and stretching in response to the presence of matter and energy. It challenges you to imagine the universe not as a static stage but as a flexible fabric whose geometry determines behavior. It asks you to accept that what you feel when you stand still is not gravity acting on you, but your body resisting the geometry around you. It invites you to see the universe not as a collection of objects, but as an interconnected system where geometry, energy, motion, and time weave together into one tapestry. By the time this story unfolds through all 17 sections, the simple idea you grew up with, gravity as a force pulling things down, will feel as outdated as believing the Earth is flat. What replaces it will be far stranger and far more beautiful, a deeper, richer, scientifically grounded understanding of the very structure of reality. And the best part is this: every mystery we uncover will lead to a new question, because gravity is not just something we experience, it is something we are still learning to understand. The journey begins now. For thousands of years before Newton, gravity was an unnamed and unexplained curiosity woven through everyday life, something people accepted without question, much like breathing or the rising of the sun. It was a familiar shadow of experience long before it became a subject of scientific investigation. Ancient civilizations noticed that objects fell when dropped, that rain returned to the ground, that smoke rose only to descend again, that the moon maintained a steady path across the sky. But these observations lived inside myth or philosophy rather than physics. Aristotle, one of history's most influential thinkers, believed that objects sought their natural place, which for heavy things meant moving downward toward the center of the earth. His view was not based on experimentation, but on intuition shaped by a world where things indeed fell. For nearly 2,000 years, this explanation dominated because no one had the tools, the mathematical framework, or the mindset to question it. The falling apple, the orbiting moon, the behavior of tides, the motion of planets, everything seemed to follow mysterious rules that eluded deeper understanding. And because no one knew how to unify them, they remained separate puzzles scattered across the intellectual landscape. The world changed when a young boy named Isaac Newton grew up during a period of intellectual transformation known as the Scientific Revolution. The 1600s were a time when old ideas were finally being challenged by evidence rather than authority. Telescopes were revealing moons orbiting Jupiter, comets were tracing unexpected paths across the heavens, and astronomers such as Kepler had discovered that planets follow elliptical orbits, not perfect circles as previously believed. Yet even with these insights, no one understood why the planets moved that way. People could describe motions, but they could not explain their cause. The sky seemed mechanical, almost clock-like, but the gears were invisible. Newton, introverted and often isolated, found himself drawn to questions others avoided. During the plague years when Cambridge University temporarily closed, he returned home to Woolsthorpe Manor and began thinking intensely about motion. While the famous story of an apple falling on his head is almost certainly embellished, Most historians agree that Newton did indeed watch apples fall and wondered why they always descended straight toward the Earth's centre and not sideways or upward. This observation was not unique. Everyone saw apples fall, but Newton did something no one else did. He connected the falling apple to the orbiting moon. That single insight sparked a revolution. Newton realized that the moon is essentially falling just like an apple, but because it has enough sideways velocity, it continually misses the Earth. In other words, the moon is in perpetual freefall, always descending but never hitting. This idea unified the heavens and the Earth in a way no previous thinker had imagined. Until then, people believed celestial bodies moved according to different rules from objects on Earth. Newton shattered that divide. He proposed that the same thing causing apples to fall was responsible for the moon's orbit, the tides, and the motion of planets. This might seem obvious today, but in Newton's era, it was a revolutionary leap of imagination. To explain this universal falling, Newton formulated his law of universal gravitation. According to him, every object with mass attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Although he did not know what gravity was physically, he had described mathematically how it acted, and the mathematics worked astonishingly well. With this single equation, Newton could explain why planets move faster when they're closer to the Sun, why comets follow long elliptical trajectories, why tides follow predictable rhythms based on the Moon's position, and why Jupiter's massive size influences the motion of its many moons. The same formula that described the fall of an apple described the dance of the cosmos. For the first time, humans had a unified law connecting the Earth to the heavens. Newton's work also introduced a new language for physics, calculus. With this mathematical invention, he could describe continuously changing motion, allowing him to analyze orbits, forces, and trajectories that had previously been impossible to compute. His approach was so powerful that it allowed astronomers centuries later to discover planets they could not see. In the mid-1800s, astronomers observed that Uranus was drifting slightly from its expected path. Something seemed to be tugging on it. Using Newton's equations, Adams and Leverrier independently calculated the position of an unseen planet. Telescopes were pointed exactly where the math predicted, and Neptune emerged from the darkness. Newton's law predicted a planet before humanity ever saw it. Few moments in the history of science demonstrate such confidence in a theory's accuracy. Yet for all Newton accomplished, he admitted that he did not know what gravity truly was. He famously wrote, "Hypotheses non fingo, I frame no hypotheses," about the deeper nature of gravitational attraction. He knew the mathematics but not the mechanism. How could two objects exert a force across empty space? Why should the Sun influence Earth from millions of kilometers away without a physical connection? Newton had no satisfying answer. He simply stated that the equations worked and left the deeper cause for future generations to uncover. For nearly 200 years, physicists accepted Newton's description because it was extraordinarily accurate, but the philosophical discomfort remained. The idea of action at a distance, of forces reaching across the void without anything transmitting them, felt incomplete. This tension became more pronounced as scientists made increasingly precise observations. For example, Mercury's orbit did not align perfectly with Newtonian predictions. It precessed, rotated slightly more than expected. The discrepancy was tiny, but it was real, amounting to about 43 arcseconds per century. Some astronomers proposed an unseen planet named Vulcan orbiting near the Sun, but no such object existed. Newton's laws could explain almost everything, but not Mercury's orbit. For generations, this mismatch remained a puzzle. Newton's theory also had difficulty explaining why all objects fall at the same rate. In everyday experience, heavier objects appear to fall faster because of air resistance, but when air is removed, a feather and a hammer fall identically. Galileo demonstrated this principle conceptually, and astronauts confirmed it on the Moon. Newton's laws allowed this behavior mathematically, but they did not explain why gravitational mass and inertial mass were perfectly equivalent. This equivalence seemed like an improbable coincidence, one that hinted at a deeper truth. Another conceptual limitation lay in the nature of time and space. Newton assumed space was absolute, a fixed stage unaffected by events, and time was universal, flowing at the same rate everywhere for everyone. These ideas matched intuition, but intuition is not always a reliable guide. Under Newtonian gravity, space and time remain unaffected by mass and motion, yet gravitational attraction required instantaneous communication across space. This contradicted the emerging understanding of electromagnetism, which showed that signals could travel no faster than the speed of light. Newton's gravity operated outside this constraint. Something had to give. Despite these flaws, Newton's theory remained the best available framework for centuries. It guided navigators, engineers, astronomers, and explorers. It predicted the return of Halley's Comet. It explained the structure of Saturn's rings, the stability of planetary orbits, and the behavior of pendulums. Practically speaking, Newton's equations still work extremely well for most everyday applications. We use them in engineering, spacecraft trajectory planning, bridge construction, ballistics, robotics, and nearly any context where relativistic effects are negligible. Even today, most calculations in physics classrooms begin with Newton because it remains a remarkably accurate approximation of gravitational behavior under typical conditions. But the elegance of Newton's work often leads to oversimplified stories. The famous tale of the apple hitting Newton's head is almost certainly exaggerated, though he did later write about observing apples fall. The notion that Newton suddenly understood gravity in a single moment of inspiration is also a myth. His insight came from years of contemplation, mathematics, and comparison of astronomical data. And although Newton is sometimes portrayed as a lone genius, he built upon the work of Kepler, Galileo, Hooke, Descartes, and others. Science is never the accomplishment of one person. Newton once wrote, "If I have seen further, it is by standing on the shoulders of giants." Yet even those giants could not solve the deeper mystery. What actually causes gravity? It is one thing to describe how objects move. It is another to explain why they move that way. Newton's description lacked a mechanism. He treated space as a stage and gravity as a force. Einstein would later show that gravity is geometry, that space and time merge into a single fabric that curves in the presence of mass and energy, and that objects follow the curves naturally. Newton's view assumed absolute space, but Einstein revealed that space is dynamic. Newton's view assumed absolute time, but Einstein showed that time depends on motion and gravity. Newton imagined gravity as a force acting at a distance, but Einstein revealed it as a manifestation of curvature. The two theories are not enemies, they are layers. Newton's theory works where spacetime curvature is small and velocities are modest. Einstein's theory takes over when curvature becomes significant or when motion approaches the speed of light. The transition from Newton to Einstein does not diminish Newton's brilliance. Instead, it highlights the structure of scientific progress. Powerful ideas refined, expanded, and sometimes transformed by deeper understanding. Newton built the foundation. Einstein extended the architecture. The physicists of today attempt to construct the next level, a theory that unifies gravity with quantum mechanics and explains what spacetime truly is. But before Einstein reshaped our picture of the universe, Newton reshaped our picture of motion. He unified the heavens and earth under one law. giving humans the first glimpse of a universe governed by universal principles rather than myth or intuition. His equations unlocked the path to modern astrophysics, cosmology, and gravitational science. They remain embedded in every engineering project, every spacecraft mission, and every basic physics lesson. They are not wrong, they are limited. And those limitations, subtle though they may be, open the door to the deeper question. If gravity is not a force, if space and time are not absolute, and if attraction is really curvature, then what is the true engine behind the universe's motion? That question leads directly into the next chapter of gravity's story, the moment when Einstein looked at Newton's framework, saw its brilliance, saw its cracks, and began constructing a new vision of reality that would turn gravity into something far stranger and far more beautiful than anyone before him had imagined. When Einstein began re-examining gravity, he did not set out to overthrow Newton. He admired Newton deeply and understood the power of the mathematical framework that had governed physics for more than 2 centuries. Yet Einstein sensed that Newton's model, for all its elegance, concealed a deeper level of truth. Newton had described gravity as a force acting across space, but he had not explained how that force travelled or why mass exerted influence at a distance. Einstein wanted clarity. He wanted a picture of the universe that left no room for mysterious pulls. He wanted a vision of reality in which motion, time, and space all emerged from consistent principles. It was not obvious where this journey would lead, but it began with one idea so simple that it seems almost trivial at first: the experience of falling. Imagine you're in a sealed elevator with no windows. If the elevator cable suddenly snaps and you fall freely, everything inside the elevator, including you, begins to float. You would feel weightless. Objects you let go of would hover beside you. You would not be able to tell whether gravity had vanished or whether the elevator was accelerating downward. This simple thought experiment led Einstein to a profound realization. Free fall eliminates the sensation of gravity entirely. The downward acceleration of the elevator cancels out the gravitational acceleration of every object inside it. As long as the elevator falls perfectly, everything behaves as though there is no gravity. Einstein later said that this was the happiest thought of my life, not because of its simplicity, but because of what it implied, that gravity might not be a force at all, but an effect of motion through a deeper structure. If falling makes gravity disappear, then perhaps gravity is not something acting on objects, but something objects experience when they are prevented from falling. This insight led Einstein to question the nature of inertia, acceleration, and weight. When you stand on the ground, you feel heavy, not because gravity is actively pulling on you, but because the ground is pushing up on you, preventing you from following your natural path through space-time. When you sit in a car that suddenly accelerates forward, you feel pressed back not because a force pushes you, but because your body resists the change in motion. Einstein noticed that these two sensations, weight and inertial resistance, felt exactly the same, and they did so because at a deeper level, they were the same phenomenon. Gravitational mass and inertial mass were identical in every experiment ever performed. This equivalence was not a coincidence. It pointed toward a unified explanation. The geometry of spacetime determines the motion of objects, and what we interpret as gravity is simply the manifestation of that geometry. If gravity is geometry, then the universe is not a static grid of space and time, as Newton imagined. Instead, space and time merge into a single four-dimensional entity called spacetime, which bends and stretches depending on the presence of mass and energy. This bending is not metaphorical, it is real. It affects the paths objects follow, it affects the rate at which time flows, it affects the behavior of light. When a massive object like Earth sits in space-time, it changes the geometry around it, creating curvature. Objects nearby follow the curved paths naturally, much like marbles rolling around a depression on a rubber sheet. But the sheet analogy is imperfect because it uses gravity to explain gravity. The real curvature exists in 4 dimensions, not 2, and it shapes motion without requiring any external force. In this new view, objects are not pulled toward Earth. They move along geodesics, the straightest possible paths through curved spacetime. If the ground were not in the way, you would follow your geodesic by falling freely. The ground interrupts this natural motion and exerts a force upward, and that upward force is what you feel as weight. This shift in perspective resolves the mystery of freefall. When you fall, nothing is pushing or pulling you. You are simply moving naturally, without resistance, through curved spacetime. Weight appears only when something prevents you from following your geodesic. To fully describe this geometric universe, Einstein needed a new kind of mathematics, tensor calculus, which had been developed by mathematicians such as Riemann and Ricci decades earlier, but had not yet found a major physical application. Riemann had shown that space itself could be curved, and his equations described the geometry of such curvature. Einstein realized these mathematical tools could describe not just space, but spacetime. Gravity, in this picture, was identical to curvature. The presence of mass and energy determined the curvature, and curvature determined motion. This relationship became the core of general relativity. Einstein's field equations did not resemble anything in Newtonian physics. They were complex, non-linear, and almost impossible to visualize, yet they yielded predictions that could be tested. One of the earliest successes came with Mercury. Einstein calculated the precession of Mercury's orbit using his new equations and found that the result matched the observed discrepancy exactly. Mercury's strange behavior was not due to an unseen planet or a flaw in Newton's math. It was a consequence of space-time curvature near the Sun. This was the first major confirmation of Einstein's theory, and it resolved a mystery that had persisted for decades. But the true test came during a solar eclipse in 1919. According to general relativity, light passing near a massive body should bend because the curvature of spacetime alters its trajectory. Newtonian physics also predicted a small deflection, but Einstein predicted twice that amount. During the eclipse, when the sun's light was blocked, astronomers could photograph stars near the sun's limb. Their positions shifted by exactly the amount Einstein had predicted. Newspapers around the world announced that Newton had been overturned, and a new age in physics had begun. The reaction was dramatic, sometimes exaggerated, but the data spoke clearly. General relativity described the universe more accurately than Newtonian gravity. Yet Einstein's work did not merely refine our understanding of how objects move. It transformed our understanding of time itself. In general relativity, time is not universal. It flows at different rates depending on gravitational potential. A clock closer to a massive object ticks more slowly than a clock farther away. This phenomenon is not hypothetical. It has been measured with atomic clocks separated by only centimeters in height. Time dilation affects GPS satellites. Engineers must correct for it constantly, or navigation systems would drift by kilometers. The slowing of time near massive objects plays a crucial role in black hole physics, where extreme curvature creates horizons beyond which even light cannot escape. Einstein's equations also predicted black holes long before anyone believed they could exist physically. According to the equations, if mass becomes dense enough, it curves spacetime so severely that nothing can escape the region, not even light. Many scientists dismiss this as a mathematical curiosity rather than a real phenomenon. Einstein himself was unsure, but over time, evidence accumulated. The motions of stars near the center of the Milky Way revealed an object 4 million times the mass of the Sun, packed into a region smaller than our solar system. Observations of gravitational waves revealed mergers of massive black holes billions of years old, and images from the Event Horizon Telescope revealed the shadow cast by a supermassive black hole in another galaxy. All these observations confirmed that Einstein's predictions, strange as they were, matched reality. Despite its power, general relativity is not without limitations. It breaks down at singularities where space-time curvature becomes infinite. It cannot describe the earliest instant of the universe, known as the Planck epoch, where quantum effects dominate. It fails to explain dark matter and dark energy, which together account for about 95% of the universe's mass-energy content. Einstein sought unity between gravity and electromagnetism, but did not succeed. Modern physicists seek unity between gravity and quantum mechanics, but no theory has been verified experimentally. The mathematics of quantum gravity, whether through string theory, loop quantum gravity, or emergent gravity models, remain speculative. They attempt to address the breakdown of general relativity at extreme scales, but none have achieved the universal acceptance that Einstein's theory enjoys. Still, general relativity remains the most precise description of gravity ever devised. It explains why planets move the way they do, why light bends, why time dilates, why stars evolve, why galaxies rotate, and why gravitational waves ripple through the universe. It offers a framework for understanding cosmic evolution, the expansion of space, and the large-scale structure of the cosmos. It tells us that gravity is geometry, and that geometry is dynamic. Einstein's shift from force to curvature reshaped our sense of reality. It replaced the idea of a flat, unchanging space with a living fabric that responds to mass and energy. It replaced the idea of time as a universal clock with the realization that time is personal, tied to motion and gravity. It replaced the notion of gravity acting across empty space with the idea that there is no empty space, only space-time, whose shape determines the behavior of everything within it. Einstein did not destroy Newton's work. He revealed its domain of applicability and provided a deeper layer beneath it. Newton's equations remain valid as approximations in weak gravitational fields and low velocities. Einstein's equations take over in strong fields, at high speeds, and in situations where curvature matters. The journey from Newton to Einstein is a journey from simplicity to complexity, from intuition to counterintuition, from forces to geometry, from absolute space and time to relative space-time, from action at a distance to curvature as cause. And yet, this journey is not complete. Einstein revealed the structure of space-time, but he did not reveal its substance. He described how mass and energy determine curvature, but he did not explain why the universe obeys these specific equations. He offered a geometric vision of gravity, but he did not connect it to the quantum world. The stage is now set for deeper exploration. The next step is understanding how general relativity reshapes the meaning of freefall, acceleration, time, and motion. It demands that we reinterpret weightlessness, tidal forces, and inertial frames. It challenges us to re-examine concepts as fundamental as straight lines and the passage of time. Gravity is still unfolding its secrets, and Einstein's insights were only the beginning of a much larger story that continues to evolve with every experiment and every observation. When Einstein realized that gravity and acceleration were indistinguishable to anyone experiencing them, he unknowingly stepped onto the path that would redefine the meaning of motion itself. The idea was simple enough. If you are in a sealed room with no external reference, there is no experiment you can perform to determine whether the force you feel is caused by gravity or by the room accelerating upward. Your body reacts the same way in both cases. This symmetry became the foundation of what Einstein later called the equivalence principle. And although the principle appears intuitive in hindsight, it took a rare kind of imagination to recognize its power. It suggested that gravity was not a special separate force, but something intimately connected to the behavior of acceleration. And if gravity and acceleration were connected, then the natural path of objects in a gravitational field was not due to attraction, but due to geometry. The equivalence principle was the gateway to understanding freefall not as a state of downward motion, but as a state of true, uninterrupted natural motion through spacetime. Freefall is often misunderstood because people associate it with the feeling of dropping, but physically, freefall is not about falling, it is about the absence of resistance. When you jump from a height, your stomach lurches not because gravity pushes you downward, but because the ground no longer pushes upward. Your organs momentarily shift within you as the forces that normally hold them in place disappear. This is the true meaning of freefall. Everything inside you moves naturally along geodesics, the straightest possible paths in curved spacetime. When you are standing still on the ground, you feel weight because the ground is applying a force upward to keep you off your geodesic. When that support vanishes, the sensation of weight vanishes too. Freefall is not the presence of gravitational force, it is the absence of any force at all. Paradoxically, you feel gravity only when something stops you from moving naturally. This idea becomes clearer when you imagine two astronauts drifting side by side in orbit. If one astronaut gently pushes off the other, both will drift apart with constant velocities relative to each other. In Newtonian physics, this behavior is straightforward. No external forces act, so both astronauts move in straight lines. But in general relativity, those straight lines are not straight in a Euclidean sense. They are geodesics, shaped by Earth's curvature. Even without propulsion, even without external influence, the geometry of spacetime directs their motion. If their geodesics intersect, they move toward each other. If their geodesics diverge, they drift apart. In both cases, no force is acting between them. Their motion reflects the curvature of spacetime itself. Freefall is simply motion without interference. This shift in understanding also explains why astronauts appear weightless. The common misconception is that gravity is weaker where they are. But at the altitude of the International Space Station, gravity is still nearly as strong as it is on Earth's surface. The reason they float is not because gravity disappears, but because everything, the astronauts, the spacecraft, the objects inside, shares the same acceleration as they orbit Earth. If you were to drop a cup inside the station, it wouldn't fall, it would hover, because the station is falling around Earth in the same way the cup would. The astronauts are not in a gravity-free environment. They are in continuous freefall, tracing geodesics shaped by Earth's curvature. The sensation of weightlessness is a consequence of following the natural path through spacetime, unhindered by surfaces pushing back. Once you accept this, a deeper realization emerges. Weight is not a fundamental quantity. Weight is a condition produced by resistance against freefall. If you place a person on a scale, the number the scale shows is not a direct measure of gravitational force, but a measure of how hard the scale pushes upward against the person's body. If the person were in a freely falling elevator, the scale would read 0 even though gravity remained. And if the person were aboard a rocket accelerating upward in deep space, the scale might show the same reading as if they were standing on Earth, even though gravity played no role. Acceleration and gravity produce identical sensations because both correspond to deviations from geodesic motion. This equivalence allowed Einstein to create a powerful mental experiment involving two observers, one in a room falling freely through Earth's gravitational field, and another in a room accelerating upward through empty space. To both observers, the feeling inside the room would be indistinguishable. If the accelerating rocket pushed upward with an acceleration of 9.8 meters per second squared, an object dropped inside would fall to the floor just as it would on Earth. Nothing inside the room could reveal the difference. This was not a mathematical curiosity. It was a statement about the fundamental symmetry of the universe. If physics cannot distinguish between two situations, then those situations must reflect the same underlying structure. Einstein concluded that gravity and acceleration are not separate concepts at all. They are two manifestations of the same geometric behavior. In Newtonian terms, gravity acts differently on different masses only because the force scales with mass. A heavier object experiences a stronger pull, but also requires more force to accelerate, resulting in the same rate of fall as a lighter object. Newton's framework explains this numerically, but does not explain why the equality of gravitational and inertial mass exists. Einstein offered the deeper explanation. Mass follows geodesics, regardless of its intrinsic properties. Freefall motion depends on geometry, not mass. The equality between gravitational and inertial mass is a reflection of this geometric truth. This insight is so fundamental that physicists today consider the equivalence between these two masses one of the deepest and most precisely tested principles in nature. Experiments using lunar laser ranging, torsion balances, and satellite measurements have confirmed that objects fall with identical accelerations to extraordinary precision. The equivalence principle also predicts tidal forces, which emerge naturally from the curvature of spacetime. Consider two objects falling side by side toward Earth. If they are separated slightly horizontally, they gradually move closer together because geodesics converge as they approach the center of mass. If they are separated vertically, the lower object experiences slightly stronger curvature and thus accelerates faster. These relative differences in acceleration produce the sensation of stretching or compression. In Newtonian physics, tidal forces are explained by differences in gravitational force across space. In general relativity, they arise from the curvature of spacetime itself. Tidal forces are not imperfections in motion, but reflections of the geometric structure through which objects travel. This geometric picture explains why tides occur in Earth's oceans. The Moon's gravitational influence alters the curvature of spacetime around Earth, producing differential accelerations in different parts of the planet. The result is a rising and falling of ocean levels. But the deeper truth is that tides reveal the shape of spacetime across regions of varying curvature. Even everyday phenomena like fluid redistribution mirror the underlying geometry of the universe. The equivalence principle builds further insight when applied to light. If acceleration and gravity are interchangeable, then light must also respond to gravity. Consider an elevator accelerating upward in deep space. If a beam of light enters horizontally, the floor will rise toward the beam as the elevator accelerates, making the light appear to curve downward. If this happens in an accelerating frame, then by equivalence it must also happen in a gravitational field. Light curves not because it has mass, but because space-time tells it which direction to follow. This conclusion seemed radical when Einstein first proposed it, but it would later be confirmed by eclipse observations, gravitational lensing measurements, and high-resolution astronomical surveys. This leads to one of the most remarkable consequences of the equivalence principle. Gravity affects time itself. If acceleration and gravity are equivalent, then clocks in different gravitational potentials tick at different rates. A clock at the bottom of a tower runs slower than one at the top. A clock near a massive planet runs slower than one far away. This effect has been measured in laboratories, in airplanes, in satellites, and even across height differences within a single room. General relativity predicts gravitational time dilation precisely, and experiments confirm it to extraordinary accuracy. Without correcting for this effect, GPS would accumulate thousands of meters of error per day. The fact that your smartphone can tell you where you are relies on Einstein's insight that gravity warps time. These consequences reveal something profound. The equivalence principle is not just a mathematical abstraction, it is a window into the structure of reality. It tells us that Space-time is not a passive container, but an active participant in physics. It tells us that gravity is not a force but a manifestation of geometry. It tells us that what you perceive as acceleration may simply be your path through curved space-time. It tells us that time is not absolute but shaped by gravity. The equivalence principle is the backbone of general relativity, the insight that turns falling bodies, curved light, and distorted time into one coherent framework. Yet it is important to understand what the equivalence principle is not. It is not a complete theory of gravity on its own. It does not describe how curvature evolves or how matter interacts with spacetime. It does not provide field equations or predict gravitational waves. It does not explain black holes or cosmic expansion. It is a guiding principle, a conceptual foundation that hints at the structure behind gravity. General relativity builds upon it, using it to construct equations that govern curvature and motion. But without the equivalence principle, those equations would have no physical meaning. Modern experiments continue to probe the equivalence principle because any deviation from it would signal new physics beyond general relativity. If gravitational and inertial mass deviated even slightly, it might suggest that gravity interacts differently with certain types of matter, or that new fields exist in the universe. So far, no such deviations have been found. Every test confirms Einstein's insight with increasing precision, but physicists remain vigilant. Some theories attempting to unify gravity with quantum mechanics predict tiny violations of the equivalence principle. Future space-based experiments may probe these possibilities. If any violation is ever detected, it would revolutionize physics. The elegance of the equivalence principle lies in its simplicity. It takes everyday experience, falling, and elevates it to a universal truth. It reveals that the sensation of weightlessness is not an exception, but the natural state of motion. It shows that the ground beneath your feet is what creates weight, not gravity itself. It turns the world inside out by showing that gravity disappears when you move freely. And it points toward a universe where geometry, not force, dictates how everything evolves. Einstein once wrote that gravitation teaches the mind to think in a new way. The equivalence principle is the beginning of that new way of thinking. It reminds us that the universe is not built according to human intuition, but according to principles that require imagination to uncover. Freefall, acceleration, weight, and time are not what they appear. They are shadows cast by deeper geometric structures. Understanding those structures brings us one step closer to understanding gravity, not as a familiar companion, but as the hidden architecture beneath reality itself. Time, as we experience it, feels steady and universal. It seems to unfold the same way, for everyone, everywhere, without interruption. You wake, you work, you rest, and every moment feels separated from the next by a steady rhythm that gives structure to your life. But Einstein's insights shattered that comforting illusion. Time is not universal. Time is not absolute. Time is not the same for everyone. Instead, time stretches, shrinks, slows, or accelerates depending on motion and gravity. What you call time is only the rate at which your own internal clock measures change. And that rate is not fixed. It responds to the geometry of space-time, which means it responds to gravity. Gravity does not merely influence the motion of objects, it shapes the flow of time itself. And when you begin to look closely at how time behaves under gravity, the universe becomes far stranger than intuition ever allowed. The first clue that time might not be universal came not from gravity, but from Einstein's work on special relativity. In 1905, he showed that time depends on relative motion. A moving clock ticks more slowly than a stationary one. This effect, called time dilation, is not hypothetical. It has been measured using planes, satellites, and particle accelerators. But what Einstein realized next was even more extraordinary. If acceleration and gravity are indistinguishable in a small region of spacetime, And if acceleration alters the flow of time, then gravity must also alter time. This was not a minor conclusion. It was a revolutionary shift in how physicists understood the universe. Before Einstein, time was a dimension that never bent, never slowed, never changed. After Einstein, time became dynamic, flexible, and deeply intertwined with gravity. To understand gravitational time dilation, imagine two observers, one standing on the ground and another hovering high above Earth. Both carry identical clocks. The clock on the ground ticks more slowly than the clock at higher altitude because the gravitational potential near the surface is lower. Gravity affects time by warping the geometry of space-time, slowing the passage of time in regions where curvature is stronger. This effect is incredibly small in everyday life, but it is measurable. If you place two atomic clocks on a table, one near the floor and one a meter higher, the higher clock ticks a tiny bit faster. The difference is barely noticeable, but extremely sensitive experiments confirm it beyond any doubt. The idea that time flows differently depending on altitude seems absurd when you first hear it, but it becomes undeniable when you consider the evidence. In 1971, the Hafele-Keating experiment flew atomic clocks around the world on commercial airliners. When the clocks returned, they showed measurable differences compared to identical clocks left on the ground. Part of the discrepancy was due to motion, special relativity, but part came from gravitational time dilation, general relativity. Later experiments became even more precise. GPS satellites orbit Earth at an altitude where gravity is weaker than at the surface. Their onboard clocks tick faster by about 38 microseconds per day. If engineers ignored this effect, GPS systems would accumulate errors of several kilometers per hour, rendering them useless. Our ability to navigate cities, track aircraft, and deliver packages depends on adjusting satellite clocks to compensate for gravitational time dilation. Every time your smartphone tells you your location, it relies on Einstein's equations. Gravitational time dilation also plays a critical role in astrophysics. Near massive bodies, the slowing of time becomes profound. Close to a neutron star, time moves significantly slower than it does far away. Near the event horizon of a black hole, time slows to such an extreme that an external observer would see an object's motion gradually freeze as it approached the horizon. The object itself would not notice anything special as it fell, but to an outside observer its clock would slow and its light would redshift, becoming dimmer and redder until it faded. This phenomenon is not science fiction. It is an inevitable consequence of geometry under extreme curvature. Yet gravitational time dilation does more than slow clocks. It mixes the behavior of space and time in ways that blur traditional boundaries. As space-time curves, paths that would normally be straight bend inward. The geometry that slows time also alters the spatial relationships between objects. The equivalence principle tells us that freefall eliminates weight. Gravitational time dilation tells us that freefall also follows trajectories through regions of spacetime where time itself behaves differently. These concepts reinforce each other, producing a unified picture of motion in curved spacetime. When you fall freely, you move through regions where the rate of time changes gradually. The geometry compels your motion, not a force. This shift in perspective has profound implications for how we interpret the universe. Consider a distant galaxy whose light takes billions of years to reach Earth. During that journey, the light travels through regions of spacetime where curvature varies, where time flows differently, and where expansion stretches wavelengths. When we observe that galaxy, we see not just its position, but also how time behaved along the path the light took. Every astronomical observation is a measurement of spacetime's influence on time. Gravitational lenses, in which massive galaxy clusters bend the paths of light from more distant objects, create time delays. Light that travels around the cluster on different paths arrives at different times. These delays reveal information about the cluster's mass distribution. Time dilation is not a subtle effect, but a tool for mapping the universe. Despite its deep implications, gravitational time dilation often leads to confusion. Many people believe that time dilation means time is slower, as though someone watching would observe literal slow motion. But this is not how it works. Time dilation does not affect a person's internal experience. If you carried a clock near a black hole and lived there for a while, your own heartbeats, thoughts, and movements would feel normal. Your perception of time depends on your own clock. Dilation appears only when comparing your clock to someone else's, located in a different region of spacetime. Two observers separated by gravitational potential disagree on the passage of time, but neither feels anything unusual. This relativity of time is not symptomatic of malfunction, it is intrinsic to the geometry of the universe. The concept also inspires common myths. One myth claims that time dilation allows time travel. In reality, gravitational and motion-based time dilation do allow you to experience less time than someone else, but they do not allow you to revisit the past or create paradoxes. Time slows relative to observers in different gravitational conditions, but no mechanism allows a return to earlier states. Another myth claims that time stops completely at a black hole's event horizon. From the standpoint of a distant observer, clocks appear to freeze at the horizon, but the falling object itself crosses it normally and experiences no discontinuity at that moment. The idea of frozen time comes from comparing two vastly different frames of reference, not from a literal breakdown of time. Some predictions related to gravitational time dilation remain untested because they occur under conditions we cannot easily access. For example, near the singularity of a black hole, time dilation becomes so extreme that classical concepts may no longer apply. Quantum gravity theories attempt to describe what happens in this regime, but none have been experimentally confirmed. Quantum effects may alter the flow of time in ways general relativity cannot predict. Another prediction suggests that gravitational waves passing through spacetime subtly alter the ticking rates of clocks. This effect is too small to detect with current technology, but future precision experiments might reveal it. These predictions highlight the potential limits of general relativity and the need for a deeper theory. But even without reaching extreme conditions, gravitational time dilation has reshaped our understanding of the universe. It explains why the universe's expansion appears to accelerate when measured using distant supernova. Light traveling across billions of years passes through changing gravitational environments, and its redshift encodes information not just about motion, but about time dilation along its journey. The large-scale curvature of spacetime affects how light stretches and how we interpret cosmic history. Time dilation is woven into the story of cosmology as much as it is woven into the story of black holes. As we examine gravitational time dilation more closely, it becomes clear that time is not a uniform river flowing through the cosmos. It behaves more like a flexible fabric that responds to curvature. When spacetime bends, time bends with it. When curvature increases, time slows. When curvature decreases, time accelerates. Time dilation is not a curiosity, but a fundamental aspect of gravity. It is a manifestation of the fact that spacetime is not just a stage, but an active, evolving structure that shapes and is shaped by matter and energy. Einstein once wrote that the distinction between past, present, and future is only a stubbornly persistent illusion. Gravitational time dilation gives this statement physical meaning. Events that seem simultaneous to one observer may not be simultaneous to another. Intervals of time that seem equal in one region of spacetime may not be equal elsewhere. The flow of time itself becomes relative, dependent on where you are and how you move. This insight forces us to rethink concepts we once considered absolute. It shows that time is not a universal parameter, but a local measure influenced by geometry. Modern experiments continue to push the precision of time dilation measurements. Atomic clocks have become so sensitive that raising one clock by a few centimeters produces a measurable difference in its ticking rate. Future generations of clocks may detect time dilation caused by minor variations in Earth's gravitational field, allowing geophysicists to study the planet's structure in unprecedented detail. These advances show that Einstein's insights are not relics of early 20th century physics, but living principles driving technology and research today. Understanding gravitational time dilation does not merely expand your knowledge, it alters your perception of reality. It teaches that time is not something the universe provides equally to all observers. It reminds you that your experience of time is deeply personal, tied to your unique path through spacetime. It challenges the idea that time is a backdrop against which events unfold. Instead, it suggests that time is part of the architecture of reality, intertwined with space, curvature, energy, and motion. Time dilation also forces us to consider how little we truly understand. If time itself changes depending on gravity, what does that say about the nature of reality? What does it say about the origins of space-time? What does it say about the future of physics? These questions push us beyond the boundaries of established science and into a domain where new theories are born. They challenge us to imagine a universe where time emerges from deeper principles, where quantum information shapes geometry, where the flow of time is a consequence rather than a fundamental ingredient. Whether these ideas become confirmed parts of physics or remain speculative, they reflect the restless curiosity that drives scientific progress. In the end, gravitational time dilation is one of the most beautiful and profound consequences of Einstein's work. It takes something you thought you understood, time, and shows you that it behaves according to laws far richer and more subtle than intuition suggests. It reveals a universe where clocks disagree, where time bends, where the passage of moments is shaped by gravity. It reminds you that the universe is not built for human convenience, but for mathematical consistency, and it opens the door to deeper mysteries that lie ahead. Light is often imagined as the ultimate symbol of straightness, the purest example of something that travels in a direct, unwavering line across the universe. From childhood, you are told that light moves in straight paths unless something physically obstructs it. That idea feels intuitive. It seems obvious that light should not curve because it has no mass for gravity to pull on. But once Einstein rewrote gravity as geometry rather than force, this intuition collapsed. If gravity is curvature, and if curvature shapes the paths objects naturally follow, then massless objects such as photons are not exempt. They too must follow the geometry of space-time. They too must curve when space-time curves. What you perceive as the bending of light is not a mysterious force acting on it, but light following the straightest possible path in a space-time that is itself not straight. Light is straight, space-time is not. And when space-time bends, light reveals that curvature in the most dramatic way. The story begins with a simple thought experiment. Imagine you're inside a windowless rocket drifting in deep space. If the rocket suddenly accelerates upward, a beam of light entering from a side opening will no longer travel straight across the interior. Instead, because the rocket rises while the beam moves horizontally, the light will strike the opposite wall, slightly lower than where it entered. To someone inside, it appears as though the light curved downward, but there is no gravitational field in this scenario, only acceleration. Einstein reasoned that if an accelerating rocket causes light to curve, then so must gravity, because he had already shown the two to be indistinguishable in small regions of space-time. This was a radical conclusion. Gravity should bend the path of light, and if space is curved around massive objects, light should not travel in Euclidean lines, but in geodesics shaped by curvature. This idea challenged centuries of assumptions. In Newtonian physics, light had no mass and therefore gravity could not act on it. But Einstein's insight did not require mass. It required only that space-time be curved, and that everything, massive or not, must follow the geometry. When Einstein completed the equations of general relativity in 1915, he calculated how much light should bend when passing near a massive body such as the Sun. Newtonian approximations predicted a small deflection. Einstein predicted double that value. The difference was significant enough to design an experiment around. And in 1919, nature provided the perfect opportunity. During a total solar eclipse, the Sun is darkened by the Moon, revealing stars that would otherwise be obscured by sunlight. If light from these stars curved as it passed near the Sun, their apparent positions in the sky would shift. British astronomer Arthur Eddington led an expedition to measure this effect. When the results were analysed, they matched Einstein's prediction, not Newton's. Light bent more than classical physics allowed, confirming Einstein's curved spacetime. Newspapers declared that Newton had been dethroned and the universe had been rewritten. While the media exaggerated the revolution, the result was nonetheless profound. Light had traced the invisible curvature of spacetime, revealing that geometry was the true engine behind gravity. But gravitational bending of light is not limited to stars near the Sun. In fact, the entire universe is filled with massive objects, stars, galaxies, clusters of galaxies that alter the paths of passing photons. Light from a distant galaxy travelling toward Earth may encounter another galaxy in its way. The curvature around the foreground galaxy bends the light, focusing, distorting, splitting, or magnifying the image. This effect is known as gravitational lensing, and it is one of the most powerful observational tools in modern astrophysics. It is not rare. It occurs constantly, everywhere, across cosmic distances. The universe is full of natural gravitational lenses sculpted by mass. The simplest form of lensing produces small distortions in the shapes of background galaxies. When astronomers observe large fields of galaxies, they find that many of their shapes appear stretched or skewed. This stretching is not due to the galaxies themselves, but due to the curvature of spacetime along the path their light took. By measuring these distortions, scientists can map the distribution of mass, visible and invisible, across vast scales. The invisible mass is dark matter. Gravitational lensing offers some of the strongest evidence for dark matter's existence, because the distortions correspond to far more mass than can be accounted for by luminous objects alone. The lensing signature does not care whether the mass radiates light. It responds only to gravity. This is why lensing has become a primary tool in constructing mass maps of galaxy clusters, cosmic filaments, and other large-scale structures. In more extreme cases, lensing creates spectacular visual effects. Sometimes a single distant galaxy appears as multiple images. Sometimes it stretches into elongated arcs. In rare cases, it forms almost complete rings known as Einstein rings. These rings occur when the distant galaxy, the intervening mass, and the observer align precisely. The intervening mass acts like a curved magnifying glass, bending the light symmetrically around it. Einstein predicted these rings in theory, but he never expected them to be observed because the alignment required seemed improbable. Yet with modern telescopes, we see them regularly. They are cosmic signatures of geometry, perfect circles drawn by the curvature of spacetime itself. The most dramatic examples of lensing occur in galaxy clusters, which contain enormous amounts of mass, both visible matter and dark matter. When astronomers observe clusters through instruments like the Hubble Space Telescope, they frequently find background galaxies stretched into long, delicate arcs. Some clusters create dozens of arcs, forming intricate patterns that reveal the mass distribution within the cluster. This is not a theoretical reconstruction, it is a direct image of curvature. The arcs show exactly where space-time is bent and by how much. By analysing the shape and orientation of these arcs, scientists reconstruct the three-dimensional distribution of mass in the cluster. They can identify regions where dark matter must be present. They can estimate the total mass of the cluster. They can study how mass shapes the universe on large scales. Lensing has become one of the most precise tools for probing the invisible. Gravitational lensing also reveals the early universe. Light from distant galaxies travels billions of years before reaching us. Along the way, it encounters curvature from intervening structures. This curvature magnifies faint galaxies, allowing telescopes to observe objects that would otherwise be too dim to detect. Without lensing, many of the earliest galaxies discovered by the James Webb Space Telescope would remain invisible. Gravity acts as a natural magnifying glass, making the early universe accessible to modern instruments. Some of the brightest high-redshift galaxies observed today owe their visibility to lensing amplification. Despite its success, gravitational lensing is often misunderstood. A common misconception is that lensing requires a physical obstruction, like glass or a medium, to bend light. In reality, nothing material interacts with the light at the point of bending. The light simply follows spacetime's geometry. Another misunderstanding is that light slows down in gravitational fields. Light always moves at the same speed locally, but the shape of spacetime alters the route it takes. The path is curved, not the speed. Sometimes people think lensing works like optical lenses, but optical lenses bend light because of refraction, changes in medium. Gravitational lenses bend light due to curvature. The physical mechanisms differ completely. There is also a myth that gravitational lensing distorts images because gravity pulls photons. This is inaccurate. Gravity does not pull photons because photons have no rest mass. Photons follow geodesics that appear curved because spacetime curves. The bending is geometric, not force-based. Lensing does not require particles, it requires geometry. General relativity predicts multiple forms of gravitational lensing. Strong lensing produces highly distorted arcs or multiple images. Weak lensing subtly distorts galaxy shapes across large fields. Microlensing occurs when small masses, such as stars or planets, cause temporary magnifications of background objects. Microlensing has been used to discover exoplanets, detect compact objects in the Milky Way, and search for certain types of dark matter. Each type of lensing provides different insights into mass distribution and cosmic structure. Lensing also confirms that the universe contains far more matter than is visible. When astronomers study galaxy clusters, they find that visible matter, stars, gas, dust, accounts for only a small fraction of the mass required to produce the observed lensing. The majority of the mass is dark matter, which interacts gravitationally but not with light. This conclusion is not an assumption, it is derived from lensing patterns. Lensing offers a direct measurement of mass, independent of luminosity. In many cases, lensing is more reliable than mass estimates derived from galaxy rotation or X-ray emissions because it directly probes curvature, rather than relying on indirect assumptions. Even more intriguingly, gravitational lensing has helped settle debates about the nature of dark matter. If dark matter were composed of large numbers of black holes or other compact objects, microlensing events would occur far more frequently. But experiments such as Mako and Eros found far fewer microlensing events than would be expected if dark matter were made of such objects. This strongly suggests that dark matter is not composed primarily of compact masses, but of particles or fields that do not emit or absorb light. Lensing shaped our understanding of one of the universe's greatest mysteries. Lensing also influences our understanding of cosmic expansion. When distant galaxies are lensed by clusters, the magnification depends on the geometry of spacetime, which in turn depends on the expansion history of the universe. By studying lensing statistics across cosmic time, scientists infer how the expansion rate changed and how dark energy shaped that evolution. In this way, gravitational lensing provides clues not only about matter, but about the accelerating expansion driven by dark energy. It becomes a tool for testing cosmological models, measuring the universe's curvature, and refining estimates of parameters such as the Hubble constant. Some predictions related to gravitational lensing remain unconfirmed but plausible. Certain quantum gravity theories suggest that extremely massive objects might lens light in slightly different patterns than general relativity predicts. If such deviations exist, they are too small to measure today, but future telescopes may detect them. Another prediction is that gravitational waves, ripples in spacetime, could also be lensed. Because gravitational waves travel through spacetime the same way light does, they should experience lensing effects such as magnification or path splitting. Lensing of gravitational waves has not yet been conclusively observed, but as detectors improve, the possibility becomes more realistic. The first detection of a lensed gravitational wave would open a new era of research, allowing scientists to map mass using waves instead of light. Despite these open questions, gravitational lensing remains one of the most solid confirmations of general relativity. Every time light bends, every time an arc forms, every time a distant galaxy appears magnified, the universe confirms that Einstein's description is correct. Lensing is not an abstraction. It is visible, measurable, and undeniable. Even amateur astronomers with modest equipment can photograph lensing by massive clusters. It is the cosmos showing its geometry in plain sight. Lensing also challenges our perception of space. The fact that distant galaxies appear distorted, not because they are unusual, but because space-time stretches their images, forces us to see the universe as a flexible, dynamic structure. It reminds us that our observations are shaped by the path light takes, and that path is shaped by curvature. We never observe the universe directly. We observe light filtered through geometry. Everything we see is affected by the shape of space-time between us and the source. The bending of light is one of the most poetic confirmations of general relativity. It takes something pure and straight and shows that straightness is not a universal truth. It reveals that geometry rules everything: motion, time, curvature, and even the paths of photons. And it forces us to recognize that the universe is not flat, not rigid, not simple. It is curved, dynamic, layered, and structured on a scale that defies easy comprehension. When Einstein proposed that gravity bends light, it was an audacious claim. Today, it is one of the most powerful tools in astronomy. It is a reminder that the universe communicates not only through particles, but through geometry. Light does not wander blindly. It reads the shape of space-time and follows the script written in curvature. Lensing is the signature of that script, the evidence that mass sculpts the pathways of photons, and that empty space is never truly empty. As we continue this journey, the next chapters will explore the most extreme consequences of curvature, the formation of black holes, the warping of space-time so severe that escape becomes impossible, and the strange interplay between time, light, and gravity at the edge of physical law. The bending of light is only the beginning. When Einstein realized that gravity alters the passage of time, another consequence emerged almost automatically, as if hidden within the equations waiting to be discovered. If time flows differently, at different gravitational potentials, then the frequency of light, which is intimately tied to the ticking of time, must also change as it climbs or descends through curved spacetime. Photons do not have mass, but they carry energy. And in relativity, energy and frequency are inseparable. When time slows in strong gravity, the rhythm of everything slows, including the oscillations of light. This means that light climbing away from a massive body loses energy, not by friction or resistance, but because it is moving into a region where time flows faster. This drop in energy appears to us as a shift toward longer wavelengths, a reddening of the light. This phenomenon is known as gravitational redshift, and it is one of the most elegant demonstrations of how deeply gravity influences even the most fundamental aspects of the universe. Gravitational redshift is not the same as the Doppler shift that occurs when a source of light moves away from you. The Doppler shift is caused by relative motion. Gravitational redshift is caused by curvature. If you shine a beam of light upward in a gravitational field, the light arrives slightly redder at the top than it was at the bottom. Conversely, if light falls into a gravitational well, it gains energy and becomes bluer. This behavior is unavoidable because in general relativity, energy must be conserved as measured by observers in different gravitational potentials. When a photon climbs upward, it must expend energy to move into a region of faster running time. This energy loss manifests as a decrease in frequency, but because photons cannot slow down, they always travel at the same speed locally. The only way to lose energy is through a change in wavelength. This is not a matter of interpretation. It is a direct prediction of Einstein's equations. The first experimental confirmation came in 1959 with the Pound-Rebka experiment, conducted in the basement of Harvard University. The experiment used gamma rays emitted from iron nuclei and measured the change in frequency between the bottom and top of a tall tower. The shift was tiny, far smaller than what unaided senses could detect, but measurable using a technique called the Mussbauer effect, which allows for extremely precise detection of small frequency changes. The results matched Einstein's predictions exactly. Gravity was proven to stretch and compress the frequency of light, confirming that time dilation affects all physical processes, including the oscillations of photons. This experiment was significant not only because it confirmed a core prediction of general relativity, but because it demonstrated that gravitational redshift is not a theoretical abstraction. It occurs over everyday distances. Even between the floor and ceiling of a room, a measurable redshift exists if one uses sufficiently precise instruments. This fact means that the flow of time and the energy of light are intimately connected at every scale. Photons constantly adjust their frequency as they move through Earth's gravitational field, even though the effect is too small to notice without sensitive equipment. Larger scales reveal the phenomenon more dramatically. For example, the Sun's gravitational field causes light emitted from its surface to be gravitationally redshifted by a small but measurable amount. Spectral lines observed from the Sun are slightly displaced compared to identical lines measured in laboratories on Earth. The redshift corresponds exactly to the predictions of general relativity. This effect becomes even more pronounced in white dwarfs and neutron stars, where gravity is far stronger. Observations of white dwarf stars show clear redshifts in their spectral lines, confirming that the intense curvature near their surfaces slows time dramatically. In neutron stars, the effect is so strong that photons struggle to escape the immense gravitational field. Their light arrives at Earth with significantly lower frequency than when it was emitted. These observations provide some of the most convincing astronomical confirmations of gravitational time dilation. Gravitational redshift also plays a fundamental role in the physics of black holes. Near the event horizon, the curvature is so extreme that light emitted just above the horizon is severely redshifted. To a distant observer, the wavelength stretches toward infinity as the emitter approaches the horizon. This leads to the appearance that objects falling into a black hole fade away and slow down, even though they themselves experience no such slowing. The redshift becomes infinite at the horizon itself, meaning no light emitted exactly at the horizon can escape with finite energy. This property is not an observational artifact, it is a mathematical and physical necessity of the geometry. Redshift encodes the curvature of spacetime so deeply that photons emitted near strong gravitational fields arrive at distant observers with dramatically altered energy. Despite its elegance, gravitational redshift often leads to misconceptions. One common misunderstanding is the idea that photons lose energy in the sense that they expend effort climbing out of a gravitational well. This is misleading because photons do not struggle or slow down. They follow geodesics at constant speed. The change in energy reflects the difference in time flow between emission and detection. Locally, the photon retains its energy. The shift becomes apparent only when comparing clocks in different gravitational potentials. Another misunderstanding is that gravitational redshift can cause light to stop entirely. While redshift can stretch wavelengths significantly, there is no mechanism within classical general relativity that halts light before it crosses an event horizon. The apparent freezing occurs only from the perspective of a distant observer. In the frame of the falling object, light behaves normally. There are also speculative extensions of gravitational redshift. Certain quantum gravity theories predict that extremely high-energy photons might experience additional, tiny deviations from classical predictions, especially over cosmological distances. These effects remain hypothetical, with no current observational support. Another speculative idea is that gravitational redshift could be modified in theories where gravity emerges from microscopic information structures. These possibilities remain unproven and must not be mistaken for established science. The mainstream consensus is clear. Gravitational redshift occurs exactly as predicted by general relativity in all situations where it has been tested. Beyond astrophysics, gravitational redshift is essential for modern technology. GPS satellites, for example, orbit at higher gravitational potentials than the Earth's surface. Their clocks tick faster due to weaker gravity, but slower due to their orbital speed. Engineers must incorporate both effects to synchronize satellite time with Earthbound receivers. If the gravitational redshift correction were ignored, GPS positions would drift by kilometers within hours. The precision required, nanoseconds per day, demonstrates how deeply embedded gravitational redshift is in our technology. The universe constantly stretches and compresses the frequencies of photons traveling between satellites and Earth, and device algorithms quietly compensate for it. Gravitational redshift also helps astronomers measure distances and masses. When light from a star passes near a massive companion, it shifts in frequency. The amount of redshift depends on the gravitational potential difference between emission and detection. By analyzing the spectral lines, astronomers can estimate the mass of the object responsible. This technique is particularly useful for binary systems where one component is compact, such as a white dwarf or neutron star. Redshift measurements allow scientists to determine the mass of objects too faint or small to detect directly. In some cases, redshift has revealed neutron stars that would otherwise remain invisible. This makes redshift a diagnostic tool as much as a theoretical prediction. On cosmic scales, gravitational redshift helps distinguish between cosmological redshift and local gravitational effects. Light from distant galaxies is stretched primarily due to the expansion of the universe, but gravitational fields along the way imprint additional shifts. The combination of these effects encodes information about the structure and evolution of spacetime. Researchers studying galaxy clusters, for instance, analyze subtle gravitational redshifts to infer the depth of gravitational wells, which in turn reveals the distribution of dark matter. Redshift is therefore a probe of cosmic architecture, allowing astronomers to map invisible structures through their influence on light. It is important to emphasize that gravitational redshift is not the same as cosmological redshift. Cosmological redshift occurs because the fabric of space itself expands, stretching wavelengths as they travel. Gravitational redshift, by contrast, occurs because photons move through regions where the flow of time changes. Although both effects stretch wavelengths, their causes differ fundamentally. Confusing them leads to misunderstandings about the nature of the universe. Gravitational redshift tells us about local curvature. Cosmological redshift tells us about the global dynamics of expansion. One of the most fascinating consequences of gravitational redshift is its connection to black hole thermodynamics. In the 1970s, Stephen Hawking showed that black holes emit radiation due to quantum effects near the event horizon. This radiation, known as Hawking radiation, is extremely faint for astrophysical black holes, but the theory relies on the same principles underlying gravitational redshift. As virtual particles near the horizon become real, some escape while others are trapped. The escaping particles must climb out of a deep gravitational well, experiencing enormous redshifts that shape the spectrum of the emitted radiation. Although Hawking radiation has not been experimentally detected, it is far too weak for current instruments. The theory is widely accepted as the most plausible extension of general relativity into the quantum regime. It demonstrates that gravitational redshift is not merely a classical phenomenon, but plays a role in fundamental physics. Even more speculative are proposals that gravitational redshift could help resolve the information paradox by encoding information about matter falling into black holes. These ideas remain controversial and highly theoretical. They should not be presented as established science, but they demonstrate the conceptual power of redshift, which connects gravity, quantum mechanics, and thermodynamics in surprising ways. Despite all its complexity, the essence of gravitational redshift can be expressed in simple terms. The deeper you are in a gravitational field, the slower time passes, and the lower the frequency of emitted light. Photons climbing upward see their internal rhythm stretched. Photons falling downward see it compressed. There is no force acting on the photon. There is only geometry and the flow of time. The photon's frequency becomes a messenger of curvature, a measurable indicator of the shape of spacetime between emission and detection. As with lensing, gravitational redshift allows us to see the curvature of the universe directly. It transforms light into a probe of geometry. Every photon that reaches you carries the imprint of the gravitational landscape it travelled through. Its wavelength is a map of spacetime, encoded in oscillations too small to sense directly, but measurable with careful analysis. The universe speaks through redshift, revealing its structure in the frequency of light. Gravitational redshift reshapes not only how we see the universe, but how we conceptualize light itself. It reveals that light is not detached from gravity. It participates in gravity by following geometric rules. It shows that energy and time are interwoven, and it reminds us that reality is governed by principles far stranger and more subtle than everyday intuition can grasp. Einstein did not merely show that gravity bends light. He showed that gravity bends time, and therefore bends everything tied to time, including the oscillations of photons. When you observe redshifted light from a distant star or galaxy, you are not just seeing something far away, you are seeing the history of its journey, the gravitational valleys it climbed out of, the curvature it traversed, the expansion of space it endured, and the geometry of the universe it revealed along the way. You are seeing a story written in wavelength. When Einstein completed the framework of general relativity, he realized that gravity was no longer something external acting on objects, but an intrinsic feature of the universe itself. The old division between space, time, and force dissolved, replaced by a single continuous fabric whose shape governed everything that moved within it. Space was no longer an empty container in which events unfolded, and time was no longer a universal clock ticking identically for all observers. Instead, spacetime became a dynamic, flexible entity that could stretch, bend, twist, and ripple. Curvature replaced force. Geodesics replaced straight-line motion. Energy and momentum replaced the notion of gravitational mass. This shift was not philosophical, but mathematical. It emerged from equations that described the universe with astonishing precision. To understand gravity, one must understand the geometry of spacetime. The first step is abandoning the idea of space as static. In Newton's vision, space was absolute, a rigid, unchanging backdrop. In Einstein's vision, space is alive. It reacts to the presence of matter and energy deforming around them. This deformation is curvature. Curvature is not metaphorical, it is measurable. It determines how objects accelerate, how time flows, and how light travels. If a star collapses, the curvature around it intensifies. If two massive objects orbit each other, curvature shifts dynamically. If the universe expands, curvature evolves on cosmic scales. Spacetime is a participant in the universe's behavior, not a passive bystander. To visualize curvature, many people imagine a rubber sheet with a heavy ball placed in the center, causing the sheet to sag. While this analogy captures the basic idea of curvature, it relies on gravity itself to produce the sag, making it circular as a true explanation. The real curvature exists in 4 dimensions, not 2. It does not require an external force to form. It arises from the presence of mass energy and is intrinsic to spacetime. The rubber sheet analogy is helpful only to the extent that it shows how curvature influences paths. But the universe does not sit on a sheet. The sheet is the structure of spacetime itself. Geodesics provide the second essential concept. A geodesic is the generalization of a straight line in curved space. If you place a marble on a curved surface and allow it to roll freely, its path corresponds to a geodesic. On a sphere, geodesics are great circles. On a saddle-shaped surface, geodesics diverge from one another. In flat Euclidean space, geodesics are straight lines. In curved spacetime, geodesics are the natural paths that free particles follow. What we call acceleration under gravity is simply motion along a geodesic. When you throw a ball, it travels along a geodesic shaped by Earth's curvature. When planets orbit the Sun, they move along geodesics in the Sun's curved spacetime. No force pulls them, they follow geometry. This raises an important point. What we interpret as gravitational attraction is really geodesic deviation. Imagine 2 nearby geodesics, 2 straightest possible paths, in curved spacetime. If curvature is present, those geodesics can converge or diverge, creating relative acceleration even though neither object experiences force. This idea explains why objects fall toward Earth. Their geodesics converge toward the center due to curvature. The objects are not being pulled inward, spacetime itself guides them. Geodesic convergence also explains tidal forces. When you stand near Earth, your feet experience slightly stronger curvature than your head because they're closer to the mass. The difference in curvature produces a stretching effect. In a black hole, this effect becomes extreme. Tidal forces near the singularity grow so strong that they can tear apart atoms. Geodesic deviation is the mathematical language of tidal effects. To quantify curvature, Einstein used tensors, mathematical objects that describe how quantities change under transformations. The curvature tensor encodes how spacetime bends. The stress-energy tensor encodes the distribution of mass, energy, momentum, and pressure. Einstein's field equations relate these 2 tensors. They state, in essence, that the curvature of spacetime at each point is determined by the total energy and momentum present at that point. The equations are not simple. They consist of 10 interrelated nonlinear differential equations that require sophisticated mathematics to solve, but their meaning can be summarized in a single line. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. Although the equations are complex, their implications unfold in elegant ways. Consider a star. The mass energy inside the star curves spacetime. The curvature creates geodesics around the star that other objects follow. If the star is dense enough, the curvature becomes so severe that not even light can escape. The field equations predict this outcome. If the star collapses further, curvature near the center grows without bound, creating a singularity. The equations also predict black holes, gravitational waves, and cosmic expansion. They describe the evolution of the universe from its earliest moments to its far future. They describe how galaxies cluster, how stars orbit, how light bends, and how time flows. All of these phenomena emerge from the geometry encoded in the field equations. Yet while curvature provides a complete description of gravitational behavior, it also challenges human intuition. Most people imagine that when an object accelerates, it must experience a force. But in general relativity, acceleration can occur without force. An object in freefall accelerates toward Earth, but it feels nothing. Conversely, an object standing motionless on the ground experiences force, because the ground prevents freefall. This inversion of intuition is hard to internalize because our senses evolved in a world where resistance, friction, and muscular effort dominate. But the mathematics is clear. Force is deviation from geodesic motion. Gravity does not push or pull. It provides the geometric framework within which geodesics curve. A deeper understanding of curvature emerges when we examine how spacetime behaves near massive objects. Far from a planet or star, spacetime is nearly flat, and geodesics resemble straight lines. As you approach a massive object, curvature increases, making geodesics bend inward. If you map the paths of light passing near the sun, you see a slight deflection because the curvature is subtle. If you map the paths of light near a galaxy cluster, you see enormous arcs because the curvature is much stronger. If you examine behavior near a black hole, the curvature becomes so extreme that geodesics spiral inward toward the horizon. These differences illustrate how curvature influences motion across scales. Curvature also has a profound effect on time. Time flows more slowly in regions of strong curvature. Near a massive object, the geometry of spacetime stretches the flow of time. Clocks run slower. Particles decay more slowly. Light emitted from the surface of a star arrives redshifted. This is not a change in the clock, but a change in spacetime. Time dilation is a measurement of curvature. When you stand on Earth's surface, you experience a different flow of time than someone in orbit. The difference is tiny but measurable. This phenomenon becomes dramatic near black holes. Time near the event horizon slows to such an extent that it appears to freeze from an outside perspective. Curvature reshapes time as easily as it reshapes space. The geometry of spacetime can even twist. Rotating masses drag spacetime around them, a phenomenon known as frame dragging. This effect is predicted by general relativity and has been confirmed experimentally by satellites like Gravity Probe B. Near a rotating black hole, frame dragging becomes extreme, creating regions where space itself rotates faster than light can counteract. Objects caught in this region must rotate with the black hole, whether they want to or not. This behavior is not force-driven. It arises from the geometry of a rotating spacetime solution known as the Kerr metric. The existence of ergospheres, where objects cannot remain still relative to distant observers, shows that curvature does not merely bend space, it can twist it. Some misconceptions about curvature persist, even among science enthusiasts. One myth is that curvature requires mass. In reality, energy, momentum, pressure, and even stresses contribute to curvature. Radiation curves spacetime. Electromagnetic fields curve spacetime. A box of hot gas curves spacetime more than a box of cold gas because heat contributes energy. The stress-energy tensor includes all forms of energy, not just mass. This is why cosmological models treat dark energy as a contributor to curvature, even though it is not matter in any conventional sense. Another misconception is that curvature can be visualized only through analogies like rubber sheets. This is a useful teaching tool, but ultimately misleading. Curvature is a property of the metric, the mathematical function that measures distances and durations in spacetime. It does not require embedding in a higher dimensional space for its meaning. Speculations about curvature often wander into the realm of higher dimensional theories. Some models propose that gravity propagates into extra dimensions, which could explain why gravity appears so weak compared to other forces. Other theories suggest that spacetime is emergent, arising from microscopic quantum interactions. In such theories, curvature might not be fundamental, but a large-scale manifestation of deeper structures. These ideas are mathematically motivated, but not experimentally confirmed. They remain possibilities, not truths. The current scientific consensus is that general relativity accurately describes curvature in all situations where it has been tested, from GPS satellites to black hole mergers. Despite its success, general relativity does not answer every question about curvature. Singularities remain mysterious. At a singularity, curvature becomes infinite, and the equations break down. This suggests that general relativity is incomplete at extremely small scales or extremely high densities. Quantum gravity theories attempt to resolve these issues by quantizing spacetime itself. Some propose that spacetime is composed of discrete units that smooth out singularities. Others propose that curvature near singularities becomes finite due to quantum effects. But these ideas remain speculative until experiments or observations confirm them. Nevertheless, the geometry of spacetime remains one of the most beautiful and powerful concepts in physics. It unifies gravity, motion, and time under a single framework. It reveals the universe as a tapestry woven by energy and shaped by curvature. It provides a lens through which we interpret cosmic structure, black holes, gravitational waves, and the cosmic expansion. It allows us to calculate orbits, predict lensing patterns, model galaxy formation, and trace the evolution of the universe itself. Everything that moves does so through curvature. Everything that ages does so according to curvature. Everything that interacts with gravity is participating in geometry. When you walk, your body follows geodesics modified by the ground's resistance. When you look at the stars, their light has been bent by curvature along its journey. When you measure time, your clock ticks according to the curvature where you stand. When you watch videos from GPS satellites, the signals arrive adjusted for curvature. When you observe black holes merging billions of light years away, you are witnessing curvature dynamically rippling across space-time. The universe is geometry made manifest. Understanding curvature is understanding gravity, and understanding gravity is understanding the structure and evolution of the cosmos. Space-time is not just a stage, it is the protagonist. Einstein's reimagining of gravity as curved space-time carried with it an unexpected consequence, one that even he did not fully appreciate at first. If space-time behaves like a dynamic fabric that bends and twists in response to mass and energy, then any violent change in the distribution of mass should create ripples in that fabric, much like ripples spreading across the surface of a pond when a stone is thrown. These ripples are gravitational waves. They propagate at the speed of light, carrying information about the catastrophic events that generated them. Unlike electromagnetic waves, which can be blocked, absorbed, scattered, or distorted by matter, gravitational waves travel almost entirely unhindered. They pass through stars, planets, dust clouds, and even entire galaxies with barely any loss of energy. This makes them pristine messengers from regions of the universe that would otherwise remain invisible. including black hole interiors, supernova cores, and the earliest moments after the Big Bang. Yet despite their profound significance, gravitational waves remained undetected for a century after Einstein predicted them, because the distortions they cause in spacetime are unimaginably tiny. To understand gravitational waves, imagine two massive objects orbiting each other, such as neutron stars or black holes. Their motion continuously changes the curvature of spacetime around them. As they orbit, they send out ripples of spacetime distortion in all directions. These waves carry energy away from the system, causing the orbiting objects to gradually spiral inward. This spiral continues until they eventually collide or merge. The energy lost to gravitational waves is enormous in total, yet the waves themselves produce only minuscule stretching and squeezing of space by the time they reach Earth. For a passing gravitational wave, distances change by less than the width of a proton over kilometers. No human senses can detect such distortions. Only extremely precise instruments can. Einstein himself wavered about gravitational waves. At first, he believed they existed. Then he doubted whether they were physically real or merely mathematical artifacts. Later, he returned to the conclusion that they were real but immeasurably small. His hesitation was not due to confusion, but due to the subtle nature of the equations. Spacetime curvature is not a simple thing to describe, and distinguishing genuine physical waves from coordinate illusions took decades of refinement. Eventually, physicists agreed that gravitational waves are real, that they carry energy and that they interact with matter, very weakly but not zero. The challenge became detecting them. Indirect evidence for gravitational waves came in 1974 with the discovery of the Hulse-Taylor binary pulsar. Two neutron stars orbit each other in an extremely tight system. Their orbits gradually shrink over time at a rate nearly identical to the energy loss predicted by gravitational wave emission. The agreement between theory and observation provided the first solid confirmation that gravitational waves were not just theoretical constructs, but physical entities that influence astrophysical systems. Hulse and Taylor won the Nobel Prize for this discovery, but this was still indirect. Astronomers wanted direct detection, the passing of a gravitational wave through a detector on Earth. To detect gravitational waves, physicists built instruments known as interferometers. These devices use laser beams traveling back and forth along long perpendicular arms to measure slight changes in distance caused by passing waves. A gravitational wave slightly stretches one arm and compresses the other. When the beams recombine, the interference pattern reveals these tiny changes. The most advanced of these detectors is LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO consists of two facilities located thousands of kilometers apart, one in Louisiana and one in Washington state. Both have vacuum chambers 4 kilometers long, housing laser paths that can detect distortions smaller than 1/10,000th the diameter of a proton. Achieving this sensitivity required decades of engineering, isolation from seismic and thermal noise, sophisticated data analysis algorithms, and international collaboration. On September 14, 2015, LIGO detected its first gravitational wave, a faint chirp lasting only a fraction of a second. The signal came from two black holes, one about 36 times the mass of the Sun and the other about 29 times the mass of the Sun, spiraling together and merging over 1 billion light-years away. As the black holes approached one another, they emitted increasingly powerful gravitational waves in a rising frequency pattern. When they merged, they released more energy in gravitational waves in a fraction of a second than all the stars in the universe emit in light at that moment. The resulting distortion in spacetime reached Earth and shifted LIGO's mirrors just enough to be detected. This event, known as GWACE 5914, confirmed Einstein's prediction beyond doubt. It opened a new era in astronomy, one in which scientists could observe the universe through gravitational signals rather than light. The significance of this moment cannot be overstated. For the first time in history, humans detected vibrations in spacetime itself. We were no longer limited to observing electromagnetic waves, radio, infrared, visible, ultraviolet, X-rays, and gamma rays. We now had a direct channel to observe phenomena that produced no light at all. Black hole mergers, neutron star collisions, exotic compact objects, and even hypothetical primordial gravitational waves from the early universe all became potential sources of information. LIGO quickly followed up with many more detections, identifying additional black hole mergers, neutron star mergers, and potentially mixed systems involving one of each. As LIGO improved its sensitivity, and as additional observatories such as Virgo in Italy and Kagra in Japan came online, detection rates increased steadily. The 2017 detection of a neutron star merger, GW170817, was a particularly revolutionary event. It produced gravitational waves and electromagnetic signals, allowing astronomers to observe the same event using multiple types of radiation. The collision produced kilonova explosions, heavy elements like gold and platinum, and a burst of gamma rays. The arrival times of the gravitational waves and gamma rays match predictions. This gave scientists insights into the speed of gravitational waves, which turned out to be the speed of light, as Einstein predicted, and offered clues about the behavior of matter at nuclear densities. It also helped confirm that neutron star mergers are a major source of heavy elements in the universe. Yet gravitational waves are not limited to catastrophic events. Theory predicts that many systems produce them, though at levels far too weak for current instruments to detect. For example, rotating neutron stars with irregularities on their surfaces emit continuous gravitational waves. Turbulence in the early universe may have produced primordial gravitational waves. Binary systems of white dwarfs emit waves detectable by future space-based detectors. Even the combination of thousands of small sources may create a stochastic gravitational wave background, a faint hum permeating the universe. These predictions remain speculative to the extent that they are not yet directly observed, but every model consistent with general relativity supports their existence. One of the most exciting frontiers involves space-based detectors such as LISA, the Laser Interferometer Space Antenna. LISA will consist of 3 spacecraft separated by millions of kilometers, using laser interferometry to detect lower frequency gravitational waves that ground-based detectors cannot observe. These waves come from massive black hole mergers, galactic binaries, and possibly signals from cosmic strings or early universe processes. LISA will allow scientists to probe phenomena inaccessible to terrestrial detectors. It represents the next major breakthrough in gravitational wave astronomy. Gravitational waves also provide a unique way to test general relativity. If the waves travel at speeds other than light, or if they disperse, or if their polarization differs from predictions, it could reveal physics beyond Einstein's theory. So far, every detected signal matches general relativity with remarkable accuracy. But there is always the possibility that future observations will reveal deviations. Some theoretical models predict small differences in wave propagation, such as modifications caused by hypothetical massive gravitons or extra dimensions. These ideas remain speculative, with no experimental support. Still, gravitational wave detectors give scientists new ways to test the foundations of physics. Despite their importance, gravitational waves often lead to public misconceptions. One misunderstanding is that gravitational waves are waves in space rather than waves in spacetime. They do not ripple through space like waves moving through water or air. They represent changes in the geometry of spacetime itself. They stretch and compress distances, frequencies, and time intervals. Another misconception is that gravitational waves can be felt by humans or cause physical effects at everyday scales. In reality, gravitational waves passing through Earth distort distances by amounts far too small to affect people or structures. Even the strongest waves ever detected produce distortions smaller than atomic nuclei. Another misunderstanding is the idea that gravitational waves can be used to communicate faster than light. This is impossible. Gravitational waves propagate at the speed of light, and even if they could propagate faster, using curvature to send information would violate fundamental principles of causality. Some people also believe gravitational waves drain energy from Earth or shorten its orbit. The energy carried by waves that reach Earth is negligible. They are imperceptible ripples passing harmlessly through. Yet these misconceptions should not overshadow the profound implications of gravitational waves. They offer a new way of observing the universe, one that complements electromagnetic observations rather than replacing them. For example, black holes do not emit light, making them invisible except through their gravitational influence. But their mergers produce some of the strongest gravitational wave signals. Similarly, the interiors of supernova explosions are obscured by dense matter, blocking light. Gravitational waves from those cores would pass through unimpeded, revealing processes hidden from telescopes. The early universe was opaque to electromagnetic radiation until about 380,000 years after the Big Bang. But gravitational waves from the earliest moments would have propagated freely, carrying information from epochs that no other signals can reach. One of the most hopeful scientific goals is detecting primordial gravitational waves, signals left over from cosmic inflation. Inflation is a theoretical rapid expansion of the early universe, and if it occurred, it should have generated characteristic gravitational waves. These would produce subtle patterns in the polarization of the cosmic microwave background. Experiments are searching for these signatures, but they remain unconfirmed. If detected, primordial gravitational waves would provide strong evidence for inflation and open a window into physics at energy scales far beyond those achievable in particle accelerators. However, these waves have not yet been observed, and any claims about their detection should be treated cautiously unless supported by multiple independent experiments. Gravitational waves also highlight how interconnected spacetime is. It is easy to imagine mass curving spacetime locally, but gravitational waves demonstrate that curvature itself can move, travel, and carry information. A passing wave means the geometry at your location is temporarily oscillating. Distances stretch and shrink rhythmically. The effect is unimaginably tiny at Earth scale, but it reveals that spacetime is not static. It is elastic enough to support propagating disturbances. These disturbances are not distortions imposed from outside, but intrinsic changes in the geometry. They are the universe ringing like a cosmic bell. Einstein's equations allow spacetime to vibrate, and those vibrations can travel across the cosmos for billions of years before reaching Earth. The waves detected in 2015 began their journey long before multicellular life existed on our planet. They traveled through cosmic expansion, past innumerable galaxies, unaffected by matter or radiation, carrying the story of two black holes spiraling together in a distant corner of the universe. When they finally arrived, they created vibrations so slight that it took the most sensitive instruments ever built to detect them. Yet those faint ripples told us more about the universe than centuries of previous observations combined. As we progress in our understanding of gravitational waves, it becomes clear that they are not merely astrophysical curiosities. They are fundamental features of spacetime, as central to the structure of the universe as the curvature that governs motion or the expansion that shapes cosmic evolution. They reveal the dynamic nature of the universe, where geometry is not fixed but alive with motion. They confirm the deepest predictions of general relativity while offering new tools to search for its limitations. They expand our ability to observe, measure, and understand. Gravitational waves are the heartbeat of spacetime. To detect them is to listen to the universe itself. Black holes are the purest expressions of gravity, places where spacetime bends so completely that escape becomes impossible. They are not objects in the traditional sense, not spheres of matter or dense stars, but regions of spacetime in which curvature grows so extreme that the very structure of reality changes. To understand gravity deeply, one must understand black holes because they represent the boundary between what general relativity can explain and where it begins to break down. They are the most extreme laboratories nature offers, environments where the bending of time, the warping of space, and the transformation of energy occur at levels far beyond anything imaginable elsewhere in the universe. They are both the triumph of Einstein's theory and the doorway to physics beyond it. A black hole forms when massive stars exhaust the nuclear fuel that provides outward pressure against collapse. As fusion ceases, gravity dominates. The core contracts under its own weight, becoming increasingly dense. At lower masses, this contraction stops when electrons or neutrons resist further compression, creating white dwarfs or neutron stars. But for sufficiently massive stars, even these quantum forces cannot halt collapse. The core shrinks until it passes a critical threshold, creating a region where escape velocity exceeds the speed of light. Once this threshold is crossed, a boundary forms, the event horizon. The event horizon is not a surface in the usual sense. It is a geometric boundary, a point of no return. Anything crossing it, including light, becomes trapped, unable to escape. From the outside, the event horizon appears dark because no information or radiation escapes from it. But this darkness is not a surface you could touch. It is a property of space-time. The geometry inside the event horizon is unlike anything experienced in ordinary life. The curvature becomes so strong that the concepts of space and time mix in unusual ways. Outside the horizon, time flows forward and space extends outward. Inside, the radial direction becomes time-like, meaning that falling inward becomes as unavoidable as moving forward in time. You cannot choose to stop falling inward any more than you can choose to stop moving into the next moment. The singularity, a point where curvature becomes infinite, lies in the future of every object inside the horizon. This singularity is not a place in space but an end of time. It marks a breakdown of general relativity, a region where the theory cannot describe what happens. The existence of singularities is widely accepted mathematically, but many physicists believe that quantum gravity will resolve them. Yet no definitive theory currently exists. Black holes come in many sizes. Stellar mass black holes form from collapsing stars and may weigh tens of times the mass of the Sun. Supermassive black holes, found at the centers of galaxies, can weigh millions or billions of solar masses. They do not form from stars. Instead, they likely grow through mergers, accretion, and possibly seeds formed in the early universe. Intermediate mass black holes occupy the range between the two, but are harder to detect. The variety of black holes reflects the diverse environments in which gravity shapes the universe. Observational evidence for black holes is overwhelming. The first clues came from X-ray binaries, where a visible star orbits an unseen companion. The motion of the star indicates the presence of a massive object too small to be a neutron star. Later, the study of galactic centers revealed stars moving at extreme velocities around invisible objects. In our own Milky Way, stars near the center orbit a dark mass 4 million times the mass of the Sun. This object, Sagittarius A, has no visible light, no solid surface, and no alternative explanation that fits the data. The only consistent interpretation is a supermassive black hole. But the most striking confirmation came in 2019 when the Event Horizon Telescope, EHT, released the first image of a black hole's shadow. The image showed a glowing ring of hot plasma surrounding a dark region where light cannot escape. The dark center is not the black hole itself, but the photon ring, where light is gravitationally lensed around the horizon. The shape of this shadow matched predictions from general relativity with remarkable precision. This achievement required a global network of telescopes functioning as a virtual Earth-sized dish. The result was not a photograph in the traditional sense, but a reconstruction created using interferometry and computational algorithms. Yet it was a direct observation of the event horizon's effect on light, and it confirmed that black holes behave exactly as Einstein predicted. Gravitational waves provide another line of evidence. When two black holes spiral toward each other and merge, they emit powerful gravitational waves that encode their masses, spins, and dynamics. LIGO and Virgo have detected dozens of such mergers, each confirming the existence of black holes and revealing details about their population across the universe. The waveforms match general relativity's predictions with extraordinary accuracy. The final stages of the merger produce a ringing pattern called a quasi-normal mode, determined solely by the mass and spin of the final black hole. This ring-down signature is analogous to a struck bell and is uniquely characteristic of black holes. No other object produces such signals. Despite the overwhelming evidence, black holes are often misunderstood. Many people imagine that black holes suck matter like cosmic vacuums. This is incorrect. Black holes do not pull matter differently from other massive objects. A black hole with the same mass as the Sun would exert the same gravitational influence at Earth's distance. Earth would continue orbiting as before. What makes black holes unique is not their pull, but the fact that they can trap light within their horizons. Their extreme density compresses mass into a region so small that escape becomes impossible. But at a distance, their gravitational behavior is like any other mass. Another misconception is that black holes are holes in space that lead to other universes or wormholes. While wormholes appear in some solutions to Einstein's equations, they require exotic conditions, such as negative energy density, that are not known to exist in nature. No observational evidence supports the idea that black holes lead elsewhere. The interior of a realistic black hole appears to collapse toward a singularity rather than opening into another region. This does not rule out speculative theories, but they remain purely speculative, with no experimental basis. There is also a common myth that black holes roam the universe seeking matter to consume. In reality, black holes behave like any massive object. They only accrete matter that comes near enough to be captured by their gravitational field. Most black holes are quiet, with little or no accretion. Even supermassive black holes spend much of their time dormant, activated only when stars or gas clouds venture too close. When they do accrete matter, the process produces spectacular phenomena: jets, flares, disks, but these events depend on the surrounding environment rather than the behavior of the black hole itself. The physics near the event horizon reveals the most dramatic consequences of curvature. As an object approaches the horizon, time dilation becomes extreme. To a distant observer, the object appears to slow as it nears the horizon, taking an infinite amount of time to cross. Its light becomes increasingly red-shifted until it fades. In its own frame, however, the object crosses the horizon in finite time, without noticing anything special at that moment. This difference is not a contradiction, but a consequence of relativity. Observers in different frames disagree about the sequence and duration of events. To the falling object, the singularity lies ahead. To the distant observer, the object becomes part of the horizon structure. This difference leads to the concept of the frozen star, an early interpretation of black holes in which infalling matter appears to freeze at the horizon. Although this perception is correct for distant observers, it is not the physical structure of the black hole. The matter crosses the horizon and contributes to the black hole's mass, but its observable effects fade due to redshift. This subtlety often leads to confusion, but careful consideration resolves it. The horizon is a geometric boundary with different properties for observers inside and outside. Black holes also raise deep questions related to thermodynamics and quantum mechanics. In the 1970s, Stephen Hawking showed that black holes emit radiation due to quantum effects near the horizon. Virtual particle pairs constantly form and annihilate in vacuum. Near the horizon, one particle may fall in while the other escapes, creating a net emission. This Hawking radiation causes black holes to lose mass over extremely long timescales. For stellar mass black holes, the evaporation time is far longer than the age of the universe, making the effect undetectable today. But the theory is widely accepted because it follows from combining relativity, quantum fields, and thermodynamics. Black holes have temperature, entropy, and obey laws analogous to the laws of thermodynamics. These insights hint at a deeper theory in which spacetime itself emerges from quantum information. One of the most famous puzzles arising from Hawking radiation is the black hole information paradox. If black holes evaporate and disappear, what happens to the information about the matter that fell into them? Quantum mechanics forbids the destruction of information, but classical black holes appear to erase it. This conflict suggests that general relativity and quantum mechanics cannot both be correct in their current forms. Many solutions have been proposed, including holography, firewalls, and microstate geometries. These ideas remain speculative, with no experimental confirmation. Yet the paradox illustrates how black holes push the boundaries of physics. They sit at the intersection of gravity, quantum theory, and thermodynamics, revealing tensions that demand a deeper framework. Observations of black hole mergers provide additional clues. By analysing the waveforms of gravitational waves from merging black holes, scientists test whether the final black hole conforms to general relativity's predictions. So far, all detected mergers behave exactly as expected, but future detectors may reveal deviations, especially in the ring-down phase, which is sensitive to the structure of the event horizon. Some alternative theories propose that black holes might not have horizons, but instead have exotic surfaces. No such deviations have been observed. The consensus remains that black holes with horizons, as predicted by general relativity, exist and behave as expected. Black holes also influence galaxy formation. Their gravitational influence extends far beyond their immediate surroundings. Supermassive black holes regulate star formation by releasing energy into surrounding gas through jets and winds. These outflows prevent excessive cooling and collapse, shaping galaxy evolution. This connection between black holes and galaxies is one of the most remarkable relationships in astrophysics. Despite occupying tiny regions, black holes influence structures on scales millions of times larger. Another deep mystery concerns how supermassive black holes grew so quickly in the early universe. Observations from the James Webb Space Telescope reveal black holes with masses of hundreds of millions of suns, less than 1 billion years after the Big Bang. Traditional growth models struggle to explain this. Several theories exist: direct collapse black holes, rapid accretion episodes, dense star cluster collapse, but none are proven. These questions highlight the gaps in our understanding of how black holes form and evolve across cosmic history. Even the nature of the singularity inside a black hole remains unknown. General relativity predicts infinite curvature, but infinities usually signal a breakdown of theory. Many physicists believe quantum gravity will replace the singularity with a finite structure, possibly a region of extremely high but finite density. Ideas such as loop quantum gravity suggest that spacetime might have discrete structure, preventing collapse to a point. String theory suggests that extended objects might smear out the singularity. Other models propose that singularities are replaced by black hole cores described by quantum states. These models are unconfirmed. They represent educated speculation, not accepted physics. Despite the unknowns, what we do know about black holes is profound. They are real, they form in nature, they shape galaxies, they emit gravitational waves, they radiate quantum thermodynamic signatures, they challenge the foundations of physics. They exist not as exotic exceptions but as common inhabitants of the cosmos. Every large galaxy hosts a supermassive black hole at its center. Countless stellar mass black holes populate the galaxy. They are not cosmic rarities. They are fundamental products of gravitational evolution. Black holes force us to rethink everything we know about gravity. They show that space-time can fold so tightly that boundaries form. They show that time can slow nearly to a stop. They show that curvature can reach extremes unimaginable elsewhere. They show that gravity is not simply a gentle bending of paths, but a force capable of creating horizons, trapping light and reshaping reality. They reveal that Einstein's equations hold true under extraordinary conditions, and yet hint at their eventual limitations. In the story of gravity, black holes are both the culmination and the beginning. They are the most complete expression of general relativity and the clearest sign that general relativity is incomplete. They are where our understanding is strongest and where our ignorance is greatest. They are reminders that the universe is not built to satisfy human intuition, but to obey laws that are deeper, stranger, and more beautiful than anything we imagined. And as we continue to study them through telescopes and gravitational wave detectors, they will guide us toward the next revolution in physics, whatever form it takes. Around black holes and other compact objects, gravity reveals another aspect of its nature, one that transforms ordinary matter into some of the most energetic and luminous structures in the universe. When gas, dust, plasma, or even entire stars venture too close to a massive gravitational well, the infalling material does not simply plunge inward in a straight line. Instead, because almost all matter carries angular momentum, it spirals inward, forming a rotating structure called an accretion disk. These disks are not passive rings, but violent, turbulent environments where gravitational energy converts into heat, radiation, magnetic fields, and occasionally jets of plasma that extend thousands of light years into space. Accretion disks provide some of the clearest observational evidence of black holes, even though the holes themselves remain dark. They also reveal how gravity interacts with matter at extreme densities and temperatures, pushing physics to its limits. Understanding these disks means understanding the most energetic processes gravity can produce outside a singularity. An accretion disk forms because matter cannot fall directly into a compact object without losing angular momentum. As gas spirals inward, friction between its layers increases. But this friction is not like the resistance you feel rubbing your hands together. It arises from differential rotation, turbulence, and interactions between charged particles and magnetic fields. These processes create a gradual transfer of angular momentum outward, allowing some material to move closer to the black hole, while other material moves outward. The inward moving material heats as gravitational potential energy converts into kinetic energy, and then into thermal energy. The temperatures can reach millions of degrees, producing X-rays and gamma rays. This heating makes accretion disks some of the brightest objects in the universe, even brighter than entire galaxies in extreme cases known as quasars. The inner regions of accretion disks behave according to the rules of general relativity, not Newtonian physics. Close to a black hole, space-time curvature affects how matter moves, rotates, and dissipates energy. There is an innermost stable circular orbit, inside which no stable orbit exists. Matter crossing this boundary plunges inward. The existence of this orbit is a prediction of general relativity, and its radius depends on whether the black hole is rotating. Observations of accretion disks around stellar mass and supermassive black holes have provided evidence for this structure. By analysing the spectrum and variability of emitted radiation, scientists infer the position of the innermost stable orbit, confirming relativistic predictions. Rotating black holes, described by the Kerr metric, allow matter to orbit closer to the horizon, changing the disk's temperature and luminosity. These differences reveal the black hole's spin, one of its only defining properties besides mass. Magnetic fields play a major role in the dynamics of accretion disks. Even weak magnetic fields can become amplified through differential rotation, creating tangled structures that influence the motion of charged particles. Magnetorotational instability, a process discovered in the 1990s, explains how angular momentum is transported efficiently through the disk. This instability arises when the combination of rotation and magnetic fields causes small perturbations to grow exponentially, generating turbulence. The turbulence enhances the outward transport of angular momentum, enabling the inward drift of matter. Without this mechanism, accretion disks would be too stable to accrete efficiently. Magnetic fields also help channel material into jets, which remain one of the most mysterious features of accreting systems. Jets emerge from systems with accretion disks around black holes, neutron stars, and sometimes even young stars, though the power and scale differ dramatically. In the case of black holes, especially supermassive ones, jets can extend thousands or even millions of light years. They are narrow beams of plasma accelerated to near light speed, emitting radio waves, X-rays, and gamma rays. Their precise formation mechanism remains partly uncertain, but the leading theory involves the twisting of magnetic field lines near the black hole's poles. The rotation of the disk and the black hole itself winds these lines so tightly that they funnel charged particles outward. The energy for the jet may come from the accretion disk, from the rotational energy of the black hole, or from a combination of both. The Blandford-Znajek mechanism, proposed in 1977, suggests that rotating black holes can transfer some of their spin energy into the jet through magnetic fields. Although this mechanism is widely accepted among astrophysicists, direct confirmation remains challenging due to the complexity of the environment near the event horizon. Accretion disks also explain the behavior of quasars, which are among the brightest objects in the universe. Quasars appear as star-like points of light, but are actually powered by supermassive black holes, accreting matter at extraordinary rates. The light emitted from a quasar can outshine the entire galaxy hosting it. The luminous output comes not from the black hole, but from the disk. As matter spirals inward, gravitational energy releases on a scale unmatched by any other known process, except nuclear reactions inside stars. And even then, accretion can be orders of magnitude more efficient. This efficiency is why active galactic nuclei dominate the energy output of the cosmos in certain wavelengths. Observations of quasars at great distances allow astronomers to study the early universe since the light left billions of years ago. Many of the earliest quasars discovered challenge existing models of black hole growth because their masses appear large despite forming relatively soon after the Big Bang. Observational evidence for accretion disks extends across the electromagnetic spectrum. Radio telescopes detect jets and synchrotron radiation. X-ray telescopes observe the hottest inner regions. Infrared telescopes observe the cooler outer regions. Instruments like the Chandra X-ray Observatory and the New Star Telescope have captured detailed spectra that reveal disk temperature, density, and chemical composition. The Event Horizon Telescope's images of 87OX and Sagittarius A show the shadow of the black hole surrounded by a glowing ring of emission, produced by hot plasma in the disk. These images provide direct visual confirmation of matter spiraling near an event horizon. They also match numerical simulations of general relativistic magnetohydrodynamics, giving confidence in our understanding of disk physics. Accretion disks around neutron stars behave differently from those around black holes because neutron stars have solid surfaces. When matter falls onto a neutron star, it impacts the surface, producing bursts of radiation known as X-ray bursts or accretion flares. These bursts provide clues about the star's surface, density, and composition. In contrast, matter falling into a black hole emits radiation before passing the horizon, but then disappears. The absence of bursts distinguishes black holes observationally. This contrast has been used to identify black hole candidates in binary systems. Accretion does not occur smoothly. Disks can become unstable, resulting in oscillations, outbursts, or changes in luminosity. These variations contain information about the disk's structure. Quasi-periodic oscillations in X-ray binaries, for example, are believed to arise from hotspots or disk instabilities near the innermost stable orbit. Their frequencies depend on the mass and spin of the central object. Measuring these oscillations allows astrophysicists to probe the geometry of spacetime near compact objects. Such precision tests offer ways to confirm or challenge general relativity in strong field regimes. So far, observations remain consistent with relativity, though alternative theories predict subtle deviations that future telescopes may detect. Accretion disks also reveal misconceptions. One common myth is that matter falling into a black hole disappears without emitting radiation. In reality, matter releases enormous energy before crossing the horizon. The disk is the luminous structure we observe, not the horizon itself. Another misconception is that jets require the black hole to be rotating. While rotation enhances jet power, even non-rotating black holes with strong magnetic fields can produce jets. A third misunderstanding is that all accretion disks are thin and flat. In reality, disks can be thick, puffed up by radiation pressure, or warped by gravitational interactions and misaligned spins. In some extreme environments, radiation becomes trapped, creating slim disks where cooling becomes inefficient. These differences matter because they affect disk temperature, radiation spectra, and jet formation. Predictions about accretion disks continue to evolve. One prediction, supported by theory but not yet conclusively observed, is that disks around supermassive black holes may occasionally undergo large-scale magnetic reconnection events, releasing bursts of energy similar to solar flares but far more powerful. Another prediction involves the possibility that disks near rapidly spinning black holes may exhibit precession due to frame dragging, causing the entire disk to wobble. This effect, known as lens-thirring precession, is predicted by general relativity and may account for observed variations in X-ray binaries. However, conclusively isolating this effect from other variables remains challenging. Another area of active research concerns how accretion disks transition into jets. Observations show that jets appear when disks enter certain states, but the precise conditions remain debated. Some models suggest that disks must be geometrically thick and threaded by strong magnetic fields. Others argue that spin is the critical factor. The scientific consensus is that magnetic fields are essential, but the exact mechanism is still an open question. Accretion disks also relate to galaxy evolution. When supermassive black holes accrete matter intensely, they produce feedback, outflows of energy that heat surrounding gas and prevent rapid star formation. This feedback regulates the growth of galaxies. Without it, galaxies would form stars too quickly and then collapse under their own weight. This interplay between black holes and galaxies explains correlations between black hole mass and galaxy properties, such as the bulge mass or velocity dispersion. These correlations suggest that black holes and galaxies grow together, influencing each other over cosmic time. Another question involves the origin of supermassive black hole seeds. Some may grow from the remnants of massive stars. Others may form from the collapse of dense gas clouds without first forming stars. In either case, accretion plays a key role. Early accretion disks must have been extraordinarily efficient to grow black holes to millions of solar masses so quickly. Observations from the James Webb Space Telescope support the existence of early massive disks, though the details remain under investigation. This area continues to evolve scientifically. Accretion disks also teach us about extreme physics that cannot be replicated on Earth. The temperatures, pressures, and magnetic fields near black holes exceed anything achievable in laboratories. The plasma behaves according to relativistic magnetohydrodynamics, a field that blends electromagnetism, fluid dynamics, and relativity. Studying these environments reveals how matter behaves under conditions far beyond familiar experience. It also forces physicists to refine models of radiation transfer, turbulence, and plasma behavior. The innermost regions of accretion disks remain the greatest challenge. Close to the event horizon, matter approaches relativistic speeds. Light becomes strongly lensed. Time dilation alters emission patterns. Magnetic fields twist. Turbulence becomes extreme. Radiation pressure competes with gravity. Simulating these regions requires supercomputers and advanced algorithms. Yet despite these challenges, simulations have produced structures that match observations remarkably well, including the ring-like features imaged by the Event Horizon Telescope. These successes indicate that our understanding of disk physics is robust, even if incomplete. Accretion disks also help distinguish black holes from other compact objects. For example, if hypothetical exotic objects without horizons existed, such as gravitar stars or boson stars, they would produce different accretion signatures. Matter falling toward a surface would emit bursts, while matter falling past a horizon does not. The absence of such bursts provides indirect evidence for true event horizons. Future observations of the innermost disk regions may reveal even more definitive signatures. For now, the simplest and most confirmed explanation remains that astrophysical black holes possess horizons as predicted. Despite our progress, open questions remain. How exactly do disks transition into jets? What role does black hole spin play in determining jet power? How do magnetic fields behave at the event horizon? How does radiation pressure shape thick disks? How do accretion processes evolve in merging supermassive black holes? And what happens to matter once it crosses the horizon? These questions lie at the frontier of gravitational physics, astrophysics, and plasma science. Many predictions exist, but observational confirmation is required before any theory becomes part of the scientific consensus. Accretion disks remind us that gravity is not merely a quiet bending of spacetime. It can convert gravitational potential into radiation capable of traversing billions of light years. It can accelerate plasma to near-light speeds. It can sculpt jets that pierce galaxies. It can regulate star formation and shape cosmic evolution. It is dynamic, energetic, and deeply connected to the behavior of matter. When you look at an image of a glowing ring around a black hole or observe the jet of a distant quasar, you're witnessing gravity at its most intense. You are seeing matter forced into a dance, choreographed by curvature, magnetism, and turbulence. You are seeing energy unleashed through a process more efficient than any nuclear reaction. And you're seeing the universe, not as a quiet expanse, but as a place where geometry and matter meet in spectacular, violent, beautiful interactions. Accretion disks are the stage on which gravity displays its full power. Short of a singularity, they reveal what happens when matter encounters extreme curvature. They transform gravitational energy into light. They shape galaxies, power jets, produce quasars, and challenge our deepest theories. They are the luminous expression of invisible physics. Gravity is such a familiar presence that it fades into the background of daily experience, yet almost everything humans rely on, from walking to orbiting satellites to the stability of the climate, depends on its precise, predictable behavior. It is easy to think of gravity only in terms of falling objects or planetary orbits, but in reality, it silently shapes almost every aspect of the modern world, many of which people rarely associate with gravitational physics. The technologies that define contemporary life rely on subtle effects that only Einstein's theory can explain. A smartphone's navigation app, the functioning of power grids, the synchronization of global financial markets, the safety of aviation, and even the accuracy of climate models all depend on an understanding of gravity deeper than what everyday intuition offers. To see gravity not just as a cosmic phenomenon, but as an active part of modern civilization requires looking at how it infiltrates technologies, infrastructures, and natural processes on every scale. Consider, for instance, the simple act of using GPS. Most people think of GPS as a system that uses satellites to determine location through radio signals. But what makes GPS work is not just orbital mechanics, it is gravitational time dilation. The clocks aboard GPS satellites tick faster than those on Earth because they lie in a weaker gravitational field. The difference is tiny, but without correcting for this effect, GPS positions would drift by kilometers within hours. Every navigation instruction, every airplane route, every ride-sharing pickup location relies on adjusting satellite time using Einstein's equations. If general relativity were ignored, GPS would be unusable. This means that every time someone checks traffic, searches for an address, or tracks a parcel, they are using one of the most subtle consequences of curved spacetime. The same principle applies in satellite communications. Signals sent between satellites and Earth travel through regions of different gravitational potentials, and their frequencies shift accordingly. Engineers must account for gravitational redshift to maintain precise synchronization. Telecommunications networks depend on stable timing, and timing depends on gravity. Even the internet's backbone relies on time-sensitive protocols governed by atomic clocks, which must be calibrated with relativistic corrections. Gravity, in this sense, underlies the infrastructure of global communication. A similar story unfolds in aviation and spaceflight. Airplanes that fly long distances experience different gravitational potentials and speeds compared to clocks on the ground. Aviation navigation systems incorporate relativistic corrections for accuracy. When spacecraft travel to other planets, gravitational assists, a technique using a planet's motion and curvature of space to accelerate a spacecraft, enable missions that would otherwise require impossible amounts of fuel. The Voyager spacecraft, now traveling beyond the solar system, used multiple gravitational assists from Jupiter and Saturn, each time gaining velocity from the curvature of spacetime around those worlds. Without understanding gravity as curved spacetime, nearly every interplanetary mission would fail. These technologies highlight the practical consequences of relativity, but gravity also shapes the Earth itself in ways that influence everything from weather systems to geological activity. The formation of Earth's layered interior, the dense metallic core, the rocky mantle, the lighter crust, is a direct consequence of gravity pulling heavy elements inward and allowing lighter materials to rise. Without gravity's sorting effect, Earth would not have a magnetic field generated by its rotating liquid core, and without that magnetic field, life would be exposed to lethal solar radiation. Gravity drives convection in the mantle, which powers plate tectonics. Plate tectonics, in turn, shapes continents, triggers earthquakes, builds mountain ranges, and recycles carbon dioxide into the atmosphere. Without plate tectonics, Earth would resemble Mars, geologically quiet without long-term climate stability. Gravity also creates the conditions needed for an atmosphere. Air has weight because gravity holds it near Earth's surface. Without gravity, gases would disperse into space, and Earth would lose its atmosphere, oceans, and the possibility of life. The atmosphere's density decreases with altitude because gravity becomes slightly weaker as you move away from Earth's center, creating pressure gradients that shape weather patterns. Winds, storms, jet streams, and even the breathable air humans rely on all exist because gravity binds the atmosphere to the planet. The oceans behave similarly. Tides occur because the moon's gravity stretches Earth's oceans, creating bulges that move as Earth rotates. Tidal friction slows Earth's rotation very gradually, lengthening days over millions of years. Tides also influence coastal ecosystems, ocean currents, and the distribution of nutrients. The mixing of the oceans depends partly on lunar gravity. This is not metaphorical. Without tides, ocean circulation would weaken, affecting climate and the evolution of marine life. Even the stability of Earth's climate depends on gravity's precise strength. If gravity were significantly weaker, Earth could not retain a dense atmosphere. If it was significantly stronger, the atmosphere would be compressed, temperatures would rise, and chemical reactions essential for life would change drastically. On the scale of the Sun, gravity drives nuclear fusion, the process powering Earth's primary energy source. The Sun shines because gravity compresses hydrogen in its core until temperatures and pressures reach levels sufficient for fusion. Without gravity's confinement, nuclear fusion would not occur naturally. The structure of stars, the balance between gravitational collapse and internal pressure, determines their lifetimes, temperatures, and evolution. When stars exhaust their fuel, gravity determines whether they become white dwarfs, neutron stars, or black holes. Every sunset, every warm day, every growing plant owes its existence to gravity sustaining the sun's fusion. Gravity also governs the formation of planets. Dust and gas in protoplanetary disks clump together because of gravitational attraction, eventually forming planetesimals and then planets. The architecture of the solar system, its orbits, resonances, and stability emerges from gravitational interactions. Even the presence of a large moon orbiting Earth, which stabilized Earth's axial tilt and contributed to climate stability, is the result of a gravitational collision early in Earth's history. Without gravity shaping planetary systems, Earth would not exist in its present form, and neither would life as we know it. Gravity's influence extends far beyond planetary systems into the architecture of galaxies. Stars orbit galactic centers due to gravity, and the distribution of their velocities reveals the presence of dark matter, an invisible mass inferred from gravitational effects. Galaxy clusters bind together through gravity, forming the largest structures in the universe. Between these clusters lie vast voids where gravity has pulled matter away. The cosmic web itself, the pattern of filaments and clusters that defines large-scale structure, emerged from tiny density fluctuations amplified by gravity over billions of years. The universe's structure is a relic of gravity's long-term influence on matter. On human scales, we tend to think of weight as a property of objects. But in general relativity, weight is simply the reaction force preventing you from following your natural geodesic. When you stand on the ground, the surface pushes upward on you, resisting your fall through curved spacetime. This resistance is what you feel as weight. In freefall, such as astronauts in orbit, the ground no longer resists their geodesic path, and the sensation of weight disappears. This means that the feeling of weight is not caused by gravity itself, but by the interruption of freefall. This realization reshapes what it means to stand, walk, or experience physical pressure in daily life. Gravity also determines structural engineering limits. Buildings must withstand the weight imposed by Earth's gravitational field. Bridges, ships, aircraft, and skyscrapers depend on materials engineered to resist gravitational stress. Even sports, biomechanics, and human physiology are shaped by gravity's influence. Bones strengthen or weaken depending on the load they experience. Muscles adapt to gravitational stress. In microgravity environments, astronauts lose bone density and muscle mass because gravity no longer provides the mechanical stimulus that maintains them. Gravity shapes the human body at every level. In astrophysics, gravity is the dominant force over large distances, but in laboratories on Earth, gravity is among the weakest forces. This weakness allows delicate experiments in quantum mechanics, electromagnetism, and particle physics. Yet even in these experiments, gravitational effects must be accounted for when extreme precision is required. In optical clocks, gravitational potentials cause tiny shifts in frequency measurable over centimeter distances. These clocks are so precise that lifting one onto a table changes its ticking rate. This precision allows geophysicists to use clocks as gravity sensors, detecting subtle density variations beneath Earth's surface. Real-world experiments continue to test general relativity's predictions. Frame dragging, for example, was confirmed by Gravity Probe B, which measured how Earth's rotation twists spacetime slightly. Although the effect is small, its confirmation shows that even Earth's rotation influences spacetime geometry. This twisting becomes extreme near rotating black holes, but its presence on Earth demonstrates that gravity's subtler aspects operate everywhere, not only in exotic environments. Despite all this, misunderstandings about gravity persist. One common myth is that astronauts in orbit float because they are far from Earth's gravity. In reality, the gravitational field at the altitude of the International Space Station is only slightly weaker than at Earth's surface. Astronauts float because they are in continuous freefall, not because gravity is absent. Another misunderstanding is that gravity requires physical contact or force. In general relativity, nothing pushes or pulls. Gravity emerges from geometry. Another misconception is that gravity is strong because it holds planets in orbit. In fact, gravity is extraordinarily weak compared to other forces. It dominates only on large scales because it never cancels out the way electric charges do. These misconceptions obscure the elegance of gravity as a geometric phenomenon. Gravity also carries philosophical implications that reach beyond physics. It challenges the idea of space as an empty stage. In general relativity, spacetime is not passive. It responds to matter, evolves, and carries information in the form of gravitational waves. It has structure and dynamics. The fact that time flows differently depending on gravity forces us to reconsider the nature of time itself. Time is not universal, it is relational, shaped by the geometry of the universe. Every clock tells a local story, conditioned by its gravitational environment. This realization dissolves the idea of absolute time, replacing it with a web of relative durations. Gravity also reveals the interconnectedness of scales. The same curvature that governs the orbit of Earth around the Sun also governs the ticking of a clock in a laboratory. The same gravitational interaction that binds galaxies together determines ocean tides. Gravity links the cosmic and the personal, showing that everyday experiences, walking, breathing, moving, occur within a framework shaped by the same laws that sculpt galaxies. Looking to the future, gravity will play an even larger role in technology. Space-based gravitational wave detectors will map the universe in ripples rather than light. Satellite networks may rely on even more precise relativistic corrections. Quantum gravity research may one day reveal new ways to manipulate spacetime, though such ideas remain purely speculative and should not be taken as predictions of practical technology. A common unverified speculation is that gravity might allow exotic propulsion systems or wormholes, but no experimental evidence supports such possibilities. the scientific consensus remains grounded in general relativity, which continues to describe gravity with extraordinary accuracy. Even practical engineering is beginning to use relativistic effects. Precision surveying now employs gravitational corrections to measure Earth's surface more accurately. Climate models incorporate gravitational influences on ocean circulation. Future navigation systems may rely on relativistic timing at a level far surpassing today's GPS. These developments show that gravity's role in technology is expanding, not shrinking, as our ability to measure tiny relativistic effects improves. In the end, gravity's real-world importance cannot be separated from its cosmic significance. The same curvature that shapes space-time around black holes also shapes the flow of rivers. The same geodesics that guide planets also guide falling leaves. The same time dilation that affects clocks in orbit affects the lifespan of particles on Earth. Gravity connects everything: technology, biology, geology, astronomy, and philosophy. To live in a world shaped by gravity is to live inside a structure that extends from the smallest laboratory to the largest cluster of galaxies. It is to move through a geometry that determines how you stand, breathe, age, and understand the universe. Gravity is not just a cosmic force, it is the quiet architect of your daily life. And recognizing this reveals a deeper truth. Every moment, every motion, every heartbeat unfolds within a space-time shaped by the same laws that govern stars, galaxies, and the fate of the cosmos. Gravity behaves differently depending on the scale at which you observe it, revealing layers of complexity that are not obvious from everyday experience. What looks like a simple downward pull at human scale becomes, upon closer inspection, a fundamental principle shaping planets, stars, galaxies, and the entire cosmic web. The same equations describe all of these environments, yet the outcomes vary dramatically because the concentration of mass, the strength of curvature, and the interplay of forces differ across scales. Understanding gravity across these scales shows not only the universality of Einstein's theory, but also its extraordinary ability to explain phenomena that appear unrelated. From a teacup sitting on a table to the rotation of galaxies billions of light years away. What connects them is geometry, and what changes is how sharply space-time bends in response to matter. At the scale of Earth, gravity governs the environment humans directly experience. Earth's gravity keeps the oceans bound to the surface and creates the pressure gradients that enable weather patterns. It drives the formation of rivers, the settling of sediments, and the buoyancy of rocks in Earth's crust. Gravity determines how the atmosphere stays attached to Earth, how high mountains can grow before their own weight causes them to collapse, and how deep ocean trenches can become before rock begins to deform plastically. The shape of Earth itself, an oblate spheroid rather than a perfect sphere, is a consequence of rotation combined with gravity. Centrifugal force from Earth's spin slightly counteracts gravity at the equator, bulging the planet outward. Satellite measurements reveal tiny gravitational variations across Earth's surface due to differences in geological structure, water content, and crustal density. These variations help scientists study groundwater depletion, glacial melting, ocean circulation, and even the slow rebound of land after ice sheets retreat. Earth's interior structure depends entirely on gravity. When Earth formed, heavy elements like iron and nickel sank toward the center, creating the core, while lighter silicates form the mantle and crust. Without gravity's downward pull, this differentiation would not have occurred, and Earth would lack a magnetic field generated by the motion of its liquid outer core. This magnetic field protects the atmosphere from solar wind erosion. Mars, with weaker gravity and a smaller core, lost much of its atmosphere over billions of years, becoming cold and arid. Earth's stronger gravity preserved the conditions necessary for life. Even plate tectonics, one of Earth's most defining geological processes, relies on gravity driving the sinking of dense plates into the mantle. Subduction zones, mountain formation, and volcanism all depend on gravitational potential energy, and the cycling of carbon between the atmosphere, oceans, and crust depends on tectonics, indirectly influencing climate stability over millions of years. At the scale of the solar system, gravity shapes the orbits of planets, moons, asteroids, and comets. Planetary orbits follow geodesics in the Sun's curved spacetime, nearly elliptical but subtly affected by both solar mass distribution and interactions with other bodies. The stability of these orbits arises from the balance between gravitational curvature and orbital velocity. Resonances, situations where orbital periods form simple ratios, occur because gravity synchronizes motions over long timescales. For example, Neptune and Pluto are locked in a 3.2 resonance that prevents their orbits from crossing dangerously. Jupiter's massive gravity influences asteroid belts, creating gaps known as Kirkwood gaps, and shapes the migration of small bodies. The formation of planetary rings around Saturn and Jupiter results from tidal forces preventing large moons from forming within certain distances. Tidal locking, another gravitational effect, explains why the Moon always shows the same face to Earth. Over time, gravitational torque slowed the Moon's rotation until it matched its orbital period, a process still occurring for many moons elsewhere in the solar system. Gravity also controls the stability of multi-body systems. In general relativity, the more massive the central object, the stronger the curvature, and the more tightly nearby geodesics converge. This is why the solar system has a hierarchical structure. Planets orbit the Sun, moons orbit planets, and small bodies cluster according to gravitational dominance. The Lagrange points, regions where gravitational forces and orbital motion balance, represent stable or semi-stable locations where spacecraft can remain with minimal fuel. These points exist because gravity creates a landscape of potential wells and ridges, subtly shaping the motion of objects in space. Even solar system formation relied on gravity clumping dust into planetesimals and eventually planets. The architecture we observe today is the long-term outcome of gravitational interactions over billions of years. On the scale of stars, gravity plays an even more dramatic role. A star forms when gravity pulls together a dense region within a molecular cloud, causing it to contract. As the cloud collapses, gravitational potential energy converts into heat, raising the temperature and pressure at the center. When these conditions reach the threshold for nuclear fusion, a star is born. Gravity then becomes both the engine and the regulator of stellar evolution. It compresses the star's core, enabling fusion, while outward pressure from fusion counteracts collapse. This delicate balance determines a star's temperature, luminosity, and lifespan. More massive stars have stronger gravity, leading to hotter cores and faster fusion rates, making them luminous but short-lived. Smaller stars burn fuel more slowly and can live for trillions of years. Gravity also shapes the evolution of binary stars, leading to mass transfer, nova explosions, and sometimes mergers that produce unusual stellar remnants. As stars age, gravity continues to dictate their fate. When fusion ceases in the core of a Sun-like star, the gravitational collapse creates a white dwarf supported by electron degeneracy pressure. If the star is more massive, collapse continues until protons and electrons merge into neutrons, forming a neutron star. These stars, among the densest objects in the universe, compress Sun-like masses into spheres only about 20 kilometers across. Gravity at their surface is so strong that space-time curvature becomes extreme, slowing time and bending light. If the collapsing core exceeds about 3 solar masses, no known force can prevent complete collapse, leading to the formation of a black hole, where space-time curves so severely that no geodesic leads outward from within the horizon. Neutron stars represent one of the most remarkable demonstrations of gravity's power at small scales. Their densities exceed that of atomic nuclei, meaning a teaspoon of neutron star material would weigh billions of tons on Earth. Gravity holds such enormous density together, preventing the star from disintegrating. The magnetic fields of neutron stars, billions of times stronger than Earth's, arise from conservation of magnetic flux as the collapsing core shrinks. Pulsars, rapidly rotating neutron stars emitting beams of radiation, demonstrate how gravity, rotation, and magnetic fields interact to produce some of the most precise clocks in the universe. Their rotation rates slow over time due to gravitational and electromagnetic emission, and tiny irregularities in their timing provide clues about internal structure. Binary neutron star systems lose energy to gravitational waves predicted by general relativity, causing their orbits to shrink. The observed decay matches Einstein's equations with extraordinary accuracy. Black holes represent the next extreme. Their gravitational fields are so intense that they reshape spacetime dramatically. Near a black hole, the innermost stable orbit, frame dragging, time dilation, and tidal forces create environments unlike anything else in nature. The interaction between gravity and matter near the horizon produces accretion disks and jets, as discussed earlier. But from a scale perspective, black holes reveal how gravity dominates over all other forces when matter becomes sufficiently dense. Gravity becomes the architect of spacetime structure itself. Stellar mass black holes influence nearby stars in binary systems, while supermassive black holes influence entire galaxies. The scale changes, but the underlying physics remains the same. At galactic scales, gravity becomes the only significant force shaping structure, because electromagnetic forces cancel on large scales and nuclear forces act only at subatomic distances. Stars orbit galactic centers along paths determined by gravitational curvature. However, when astronomers measured the rotation curves of galaxies, they found a discrepancy. Stars far from the center orbit faster than gravity from visible matter can explain. This led to the inference of dark matter, an unseen form of mass that interacts gravitationally but not electromagnetically. Gravitational lensing by galaxy. Clusters, cosmic microwave background patterns, and large-scale simulations all support the existence of dark matter. Although it has not been directly detected, its gravitational influence is fundamental to understanding galactic scales. Without dark matter, galaxies would not form, would not hold together, and would not exhibit the rotation patterns we observe. Galaxy clusters, even larger structures, reveal gravity's influence over millions of light years. These clusters contain thousands of galaxies bound together. Their gravitational potentials trap hot gas, which emits X-rays. The distribution of this gas, combined with gravitational lensing measurements, maps the dark matter content. Collisions between galaxy clusters, such as the Bullet cluster, show dark matter and ordinary matter separating due to different collision properties. Another powerful piece of evidence for dark matter as a distinct component of the universe. Gravity sculpts the cosmic web, where matter forms filaments and nodes surrounding vast voids. These patterns emerge from tiny density fluctuations in the early universe amplified over billions of years by gravitational attraction. Gravity across scales also intersects with cosmology. The expansion of the universe, governed by the curvature of spacetime itself, depends on the total energy content, including dark energy, a mysterious component that causes accelerated expansion. Although dark energy is not gravity in the traditional sense, it influences gravitational dynamics by modifying spacetime geometry on the largest scales. The interplay between dark matter, dark energy, and ordinary matter shapes the evolution of cosmic structure. Galaxy clustering, void expansion, and gravitational lensing all respond to this combination. Gravity, in this context, becomes the storyteller of the universe's past and the predictor of its future. Yet gravity's behavior across scales also reveals mysteries not yet solved. One such mystery is why gravity is so much weaker than other forces. This hierarchy problem remains unsolved, with theories proposing extra dimensions or new particles, but none proven. Another mystery is whether dark matter consists of undiscovered particles, modified gravity, or something else entirely. Although modified gravity theories exist, the scientific consensus still favors dark matter because it explains multiple observations consistently. Another open question involves black hole singularities, regions where current equations break down. Quantum gravity may resolve these singularities, but no experimental confirmation yet exists. These unknowns highlight that gravity, while understood broadly, still contains unresolved questions across every scale. Predictions exist about gravity's behavior at untested extremes. For example, some quantum gravity theories predict changes in gravitational dynamics at incredibly small distances or extremely high energies. These predictions remain speculative because no current experiment can probe such conditions. Another theoretical prediction involves primordial black holes formed shortly after the Big Bang, which, if they exist, could contribute to dark matter. However, this remains unproven. Distinguishing between accepted science and speculative ideas is essential for maintaining clarity, especially when discussing gravity's role across scales. Despite these unresolved aspects, gravity's coherence across scales is one of its most beautiful features. The same laws that describe the fall of an apple describe the merging of black holes. The same curvature that shapes a mountain range shapes a galaxy cluster. The same geodesics that guide satellites guide gravitational waves. The universality of gravitational law means that every scale, from millimeters to megaparsecs, fits within a single, theoretical framework. Einstein's theory does not break when moving from one scale to another. It adapts seamlessly, revealing different facets of the same geometric truth. When viewed across all these scales, gravity becomes more than a force or a bending of spacetime. It is a cosmic architect, carving structure into chaos, shaping the distribution of matter, guiding the flow of time, and determining the past and future of every physical system. It binds atoms into planets, planets into solar systems into galaxies, and galaxies into the cosmic web. It sculpts landscapes, drives the evolution of stars, governs the dance of planets, and writes the history of the universe in the language of geometry. Our place within this structure is small, but the laws that govern us are the same ones that govern the larger scales. This unity across scales offers a profound sense of connection between the everyday world and the cosmic. On the largest scales imaginable, gravity becomes the quiet architect of the universe, shaping structures so vast that they defy ordinary comprehension. The night sky appears sprinkled with stars, but this impression hides a deeper truth. Stars are grouped into galaxies, galaxies into clusters, clusters into superclusters, and all of these interconnected by immense cosmic filaments stretching across hundreds of millions of light years. The pattern resembles a gigantic web, a cosmic skeleton shaped primarily by gravity's slow, persistent pull over billions of years. Even though gravity is the weakest of the fundamental interactions, it dominates the large-scale universe because it never cancels out. Positive mass always attracts. Every atom, star, and galaxy contributes to the overall gravitational field, and over cosmic time, these calculations accumulate into structures of breathtaking scale. Understanding the universe's large-scale structure means understanding gravity not as a simple attraction, but as the fundamental organizing principle of cosmic architecture. In the early universe, matter was nearly uniform, with tiny fluctuations in density no larger than 1 part in 100,000. These slight variations appear in the cosmic microwave background and represent the seeds from which all structure formed. Where matter was slightly denser, gravity pulled more matter inward, creating overdensities. Where matter was slightly less dense, gravity pulled material away, creating voids. Over billions of years, these processes amplified themselves, turning small ripples into massive structures. The result was not random. It produced a nearly universal pattern. Dense nodes connected by filaments, separated by enormous voids. These patterns persist across galaxies and clusters, forming the web-like structure of the cosmos. This arrangement is not simply a distribution of stars, but of dark matter as well, which makes up most of the mass responsible for shaping these structures. Dark matter plays the dominant role in the formation of large-scale structure because it interacts only through gravity and does not dissipate energy through radiation. Ordinary matter collapses, heats and radiates, but dark matter forms halos, extended, roughly spherical gravitational wells within which galaxies form. These halos act like scaffolding. Without dark matter, galaxies would not have enough gravitational glue to form and remain stable. Dark matter filaments guide the flow of matter across the universe, directing gas into regions where galaxies eventually ignite. Galaxy clusters sit at the intersections of these filaments, where dark matter density peaks. Although dark matter has not been directly detected and remains one of physics' greatest mysteries, its gravitational influence is undeniable. The distribution of galaxies, their velocities, their clustering statistics, and the way light bends as it travels through cosmic structures all point to the same conclusion. The universe is held together by something invisible, massive, and gravitationally influential. Galaxy clusters are among the largest bound structures in the universe, containing thousands of galaxies along with hot gas and enormous amounts of dark matter. Their gravitational complexity makes them natural laboratories for studying cosmic architecture. The hot gas in clusters emits X-rays, providing a way to map its distribution. The galaxies themselves trace only a small fraction of the mass. The true gravitational landscape is revealed through gravitational lensing, which bends the light from more distant galaxies. By examining these distortions, astronomers reconstruct the dark matter distribution within clusters. This method shows that the visible mass, stars and hot gas, is only a minor component of the cluster's total mass. Dark matter dominates the gravitational potential, shaping the motion of galaxies and the behavior of intracluster gas. One of the most striking examples of gravitational lensing in action is observed in clusters like Abell 2744, or the famous Bullet cluster. The Bullet cluster, formed from the collision of two galaxy clusters, provides compelling evidence for dark matter. During the collision, the hot gas, which makes up most of the visible mass, interacted, slowed down, and heated. The dark matter, however, passed through with little interaction, separating from the gas. Lensing maps show the dark matter leading the gas, revealing a separation that cannot be explained by modified gravitational theories alone. This observation stands as some of the strongest evidence that dark matter exists as a distinct form of mass. These collisions reveal more than just the distribution of matter. They show how gravity governs cosmic evolution. When clusters collide, gravitational potentials shift dramatically. Galaxies within the clusters are mostly unaffected because the distance between them is enormous, but the overall gravitational landscape changes. New dark matter configurations form, creating new gravitational wells. Gas is shock-heated and redistributed. The result is a dynamic reshaping of cosmic structure. Such collisions are not rare, but common over cosmic timescales. the large-scale structure of the universe is shaped not only by smooth gravitational collapse, but also by these dramatic mergers. On even larger scales, filaments of dark matter and gas connect clusters across hundreds of millions of light years. These filaments are the highways along which matter travels. They contain galaxies, gas flows, shock fronts, and complex gravitational fields. Observations with radio and X-ray telescopes reveal warm-hot intergalactic gas threading these filaments. Gravity drives the motion of this gas, pulling it toward clusters and enriching it with heavy elements from galactic winds. Filaments carry material into clusters, fueling their growth. They also carry galaxies along them, creating preferred directions of motion and shaping cluster geometry. Voids, the enormous regions of space with very low galaxy density, reveal gravity's influence by contrast. Voids are not empty, but contain dark matter and gas at lower densities. Gravity pulls matter out of voids into surrounding structures, causing voids to expand faster than the universe as a whole. This differential expansion shapes the cosmic web. The edges of voids become dense through gravitational flows, creating walls and filaments. Studying voids provides insight into dark energy because their expansion depends sensitively on cosmic acceleration. Although still an active area of research, voids offer one of the most promising methods for probing the nature of dark energy. Gravity also governs the motion of galaxies within clusters and filaments. Galaxies move at hundreds or thousands of kilometers per second, tracing orbits shaped by the gravitational potential. Observing these motions allows astronomers to infer cluster mass. Early measurements by Fritz Zwicky revealed that galaxies in clusters move too fast to be held together by visible mass alone, one of the first indications of dark matter. Modern observations then confirm this discrepancy. Without dark matter, clusters would fly apart. Instead, gravity acting on dark matter keeps them bound. Lensing reveals not only dark matter distribution, but also the history of structure formation. Strong lensing events create arcs and multiple images of background galaxies, indicating dense concentrations of mass. Weak lensing, which produces subtle distortions in galaxy shapes, traces the underlying mass distribution across large regions. Surveys using weak lensing create maps of the cosmic web, showing that dark matter forms interconnected structures aligned with theoretical predictions from cosmological simulations. These simulations, such as those performed in the Millennium Simulation or Illustris project, show how gravity sculpts structure from early density fluctuations. They begin with conditions inferred from the cosmic microwave background and evolve them forward using Einstein's equations in combination with fluid dynamics and dark matter physics. The resulting structures match observations remarkably well. Filaments, clusters, and voids emerge naturally. The agreement between simulations and observations stands as one of the greatest successes of gravitational cosmology. It demonstrates that our understanding of gravity on large scales is accurate, even though the nature of dark matter remains unknown. Despite this success, misconceptions arise about large-scale structure. One myth is that galaxies are evenly distributed throughout the universe. In reality, the distribution is highly structured, with dense clusters separated by vast voids. Another misconception is that galaxies drift apart simply due to the Big Bang's initial explosion. This picture is too simplistic. Cosmic expansion stretches spacetime itself, causing galaxies to recede, while gravity simultaneously clumps matter into structures. These opposing influences, gravity pulling inward and expansion pushing outward, shape cosmic evolution. Gravity dominates on smaller scales, forming galaxies and clusters, while expansion dominates on the largest scales. This interplay explains why structures form but do not collapse into a single mass, and also why voids continue to grow. A common myth is that dark matter must be some kind of exotic black hole or compact object. While this possibility was once considered, observations of microlensing events and cosmic structure formation show that dark matter must behave differently from ordinary matter. It does not cluster into stars or planets and does not interact with itself strongly. This does not mean dark matter is understood. It remains unknown, but its gravitational behavior is constrained by observations. Predictions exist about how large-scale structure will evolve. One prediction supported by simulations is that filaments will continue to feed clusters, making them grow while voids expand. Another prediction is that galaxies will eventually drift out of contact with one another as cosmic acceleration continues. In the far future, galaxy clusters will become gravitational islands in an expanding void. These predictions, however, depend on dark energy remaining constant. If dark energy evolves over time, a theoretical possibility, but not yet evidenced, cosmic structure formation could proceed differently. Such ideas remain speculative until observations confirm them. Gravity's influence on large-scale structure also offers clues about potential modifications to general relativity. If large-scale lensing or galaxy clustering deviated from predictions, it might suggest alternative gravitational theories. So far, observations match general relativity closely. This does not rule out alternatives, but places strong constraints on them. Any theory replacing general relativity must reproduce its large-scale predictions while also explaining cosmic acceleration. Most modified gravity theories struggle to do both. The structure of the universe also influences the propagation of light and time. Light traveling through clusters is delayed slightly due to deeper gravitational wells, an effect known as the Shapiro delay. Light is also magnified or demagnified depending on the geometry it traverses. These effects allow astronomers to measure distances independently of cosmic expansion, providing cross-checks for cosmological parameters such as the Hubble constant. The tension between different measurements of the Hubble constant remains unresolved, suggesting either systematic errors or new physics. Gravity plays a central role in this debate. Large-scale structure even influences the cosmic microwave background. Photons from the early universe pass through evolving gravitational potentials, altering their energy in an effect called the integrated Sachs-Wolf effect. This effect provides insight into dark energy and cosmic expansion. Gravity thus connects the universe's earliest light with its present-day structure. Seeing the universe on these scales reveals something profound. Gravity creates order from near uniformity. Over billions of years, it sculpts a cosmos where matter forms intricate patterns, where galaxies dance in long chains, where clusters collide and merge, and where dark matter silently shapes the unseen skeleton of the universe. This process unfolds slowly, almost imperceptibly, but its cumulative effect is majestic. The universe we observe today is the long-term imprint of gravity acting on primordial fluctuations. Across scales from Earth's interior to galactic clusters, gravity behaves with remarkable consistency. The same curvature that creates a black hole's horizon shapes the cosmic web. The same equations that describe the fall of an apple describe the evolution of the universe. This unity of behavior across unimaginable ranges of size and time is one of the most astonishing features of physics. When you look at a map of large-scale structure, you are seeing gravity's handwriting at the grandest scale. The future of gravitational physics is entering a period of rapid expansion, driven by instruments, ideas, and technologies that were impossible only a few decades ago. For most of human history, gravity was something we experienced but could not measure precisely or observe in extreme environments. Even after Newton and Einstein revealed its mathematical structure, The universe's strongest gravitational laboratories remained inaccessible, silent in their distance. That silence has now ended. Modern detectors can hear black holes collide, see the shadow of a supermassive black hole's horizon, track time dilation to millimeters, and map dark matter through the bending of starlight. The next century will push these abilities further, into realms where completely new physics may reveal itself. The key to this future is the recognition that gravity carries information not in the form of light, but in the form of curvature itself. Studying gravity's faintest ripples, deepest shadows, and earliest imprints in the cosmos will help answer questions that have remained unsolved for generations. One of the most exciting developments is the improvement of imaging techniques around black holes. The Event Horizon Telescope provided the first views of black hole shadows, revealing ring-like structures formed by the curvature of light near the horizon. Future arrays will expand the number of telescopes, increase observing frequencies, and dramatically sharpen resolution. Planned upgrades will allow images that reveal not just a single blurred ring, but time-dependent structures in the accretion flow. These could confirm predictions of turbulent plasma behavior, probe magnetic field configurations, and detect deviations from the Keir solution predicted by general relativity. Scientists hope to measure the black hole's spin more precisely, test predictions about photon rings, and perhaps detect multipole moments that differ from Einstein's expectations. If a black hole's spacetime deviates even slightly from the Keir metric, it would signal new physics or modifications of gravity in the strong field regime. Such a discovery is not predicted by the scientific consensus, but it remains a possibility that future images could reveal. For now, general relativity remains fully consistent with all available data. Gravitational wave astronomy will also expand dramatically. LIGO, Virgo, and Kagra have already opened a new window on the universe, detecting black hole mergers, neutron star collisions, and mixed systems. But the current detectors operate at limited sensitivity and frequency ranges. Future upgrades such as LIGO A+, Cosmic Explorer, and the Einstein Telescope will increase sensitivity by factors of 10 or more. These detectors will observe black hole mergers from earlier cosmic times, detect neutron star collisions at greater distances, and observe events at lower masses and frequencies. They may detect intermediate mass black holes, which have been theorized but remain observationally rare. Advanced detectors will also measure subtle deviations in gravitational waveforms, allowing tests of quantum gravity corrections, potential graviton mass limits, and alternative theories. While no such deviations have yet been detected, the next generation of observatories will bring the precision necessary to meaningfully challenge or confirm general relativity's completeness. Space-based gravitational wave detectors offer even greater potential. LISA, the Laser Interferometer Space Antenna, will consist of 3 satellites separated by millions of kilometers, measuring gravitational waves with periods of minutes to hours. This opens a completely new frequency band, enabling detection of supermassive black hole mergers, extreme mass ratio inspirals, and possibly cosmological signals from the early universe. Extreme mass ratio inspirals, where a small compact object spirals into a supermassive black hole, are especially valuable because they act as space-time probes, mapping the geometry near the horizon in exquisite detail. If general relativity fails in strong curvature environments, these waveforms will reveal it. LISA may also detect signals from hypothetical sources, like cosmic strings, though such objects remain speculative and not part of scientific consensus. If detected, they would push physics into territory far beyond current models. Even if they are not detected, LISA's data will refine understanding of galaxy evolution, black hole growth, and gravitational dynamics on scales previously unreachable. Another frontier involves detecting primordial gravitational waves, ripples produced during the universe's earliest moments. These waves, if they exist, carry information from times long before the cosmic microwave background formed. They would offer a direct test of inflation, the rapid expansion theorized to have occurred fractions of a second after the Big Bang. Experiments like CMB-S4, LIGHTBIRD, and future polarization studies aim to detect subtle patterns in the cosmic microwave background caused by these ancient waves. Their detection would not only confirm inflation, but also reveal the energy scale at which quantum gravity becomes relevant. This would be one of the deepest insights into the universe's origin ever achieved. However, primordial gravitational waves remain a prediction, not yet observed, and must be communicated as such. The scientific community remains cautious, recognizing both the challenges of measurement and the need to rule out astrophysical foregrounds that can mimic the expected signals. Testing the limits of general relativity is another major focus of future research. GR has passed every experimental test to date, from weak gravitational fields to black hole mergers. But scientists expect it to break down somewhere because it conflicts with quantum mechanics and predicts singularities where physical laws cease to function. Multiple experiments aim to find tiny deviations that could indicate new physics. Atom interferometry experiments measure gravitational effects on quantum particles with unprecedented precision, testing whether gravity behaves differently at microscopic scales. These tests could reveal hints of quantum gravity, though no deviations have yet been observed. Another direction involves searching for fifth forces or modifications to gravity that appear only under certain conditions. While these ideas are not part of the scientific consensus, they remain open possibilities that experiments can explore. Dark matter research, closely tied to gravitational physics, also shapes the future. Because dark matter reveals itself only through gravity, mapping its distribution helps constrain what it could be. Future surveys like Euclid, the Vera Rubin Observatory, and the Nancy Grace Roman Telescope will map billions of galaxies, enabling precise measurements of gravitational lensing. These maps will show how dark matter clusters, how it influences cosmic structure, and whether it behaves as expected. Some predictions involve detecting warm or self-interacting dark matter, though these models remain speculative. If deviations from the expected distribution appear, they could hint at new particles or modified gravity. However, the consensus remains that dark matter is real and behaves as cold, collisionless matter on large scales. Dark energy research also intersects with gravitational physics. The observed acceleration of the universe's expansion remains unexplained, and future experiments aim to measure this acceleration more precisely. Understanding dark energy requires mapping the universe's expansion history, galaxy clustering, supernova distances, and gravitational lensing. These measurements test whether cosmic acceleration arises from a cosmological constant, a fixed energy density, or from evolving fields or modified gravity. Modified gravity remains a minority view, but observational tests may clarify whether general relativity holds across cosmic scales. If deviations appear, they could reshape cosmology. If not, the cosmological constant remains the simplest explanation. Either way, gravity plays the central role in determining the universe's long-term fate. Another area of future research involves ultra-precise timekeeping. Atomic clocks are approaching sensitivities where gravitational variations at millimeter scales affect their ticking. Networks of clocks distributed across Earth could map gravitational potential differences in real time, enabling applications in geophysics, volcanic monitoring, water resource tracking, and underground structure detection. These technologies will integrate relativity into routine scientific and industrial applications. Timekeeping may become not just a method of synchronization, but a new kind of gravity sensor, capable of detecting subtle changes in Earth's mass distribution. Laboratory tests of gravity on extremely small scales will also advance. Current experiments test gravity down to micrometer ranges, searching for deviations from Newton's inverse square law. These deviations have not been observed, but ongoing improvements could probe deeper. Some speculative theories involving extra dimensions predict changes at sub-millimeter scales, though no experimental evidence currently supports these ideas. Testing them remains valuable because ruling out possibilities constrains new models, sharpening the path toward a quantum theory of gravity. Black hole thermodynamics, one of the most profound areas of theoretical physics, will gain new avenues for experimental testing. Hawking radiation remains too faint to observe directly for astrophysical black holes, but analog systems on Earth, such as sonic black holes in condensed matter, may reveal insights into evaporation and information retention. These analogs do not replicate gravity itself, but mimic the mathematical structure of horizons, providing clues about quantum behavior. However, they cannot confirm physics at actual black holes. They serve as conceptual laboratories, not empirical evidence. Quantum gravity remains the largest unanswered question. Multiple theoretical frameworks, string theory, loop quantum gravity, causal sets, emergent spacetime models, attempt to reconcile gravity with quantum mechanics, but none have been experimentally validated. The future of gravitational physics may provide the first data that distinguishes between them. Extreme mass ratio inspirals, primordial gravitational waves, and strong field black hole imaging offer potential insights. Yet it is equally possible that entirely new experiments, currently unimagined, will become feasible. In the history of science, major breakthroughs often come not from solving known problems, but from discovering unanticipated phenomena. Gravity, with its deep connection to spacetime, quantum theory, and cosmology, may produce such surprises. As gravitational physics advances, so will philosophical questions. If space and time are emergent phenomena rather than fundamental, then gravity may arise from deeper principles such as quantum entanglement or information theory. Some speculative models suggest that spacetime geometry reflects entanglement structure, making gravity an emergent effect of quantum mechanics. These ideas remain unproven and should not be mistaken for established science, but they highlight the growing interplay between physics and foundational questions about reality. Future experiments may provide evidence one way or another, narrowing down possibilities. Another compelling question concerns the fate of black holes. If Hawking radiation causes black holes to evaporate over trillions of years, what remains at the end? Does information survive, or is it lost? The information paradox remains unresolved, with multiple proposals but no consensus. Future gravitational wave observations may detect signatures of quantum effects at the horizon, such as post-merger echoes. These echoes are predicted by some theoretical models, but have not been confirmed. If real, they could revolutionize our understanding of quantum gravity. If not observed, they will narrow the field of viable theories. The future also includes expanding human presence in space, which will require precise gravitational navigation, advanced relativistic corrections, and deeper knowledge of gravitational environments. Long-term space habitats will need to manage artificial gravity through rotation or other methods, since prolonged exposure to microgravity weakens bones and muscles. Understanding gravity's influence on biology will become increasingly important. On planetary surfaces with lower gravity, such as Mars or the Moon, human physiology may change in unpredictable ways. Settlements will need to adapt. Gravity, far from being a background constant, will shape the evolution of human civilization. As new data accumulates, scientific consensus will evolve. General relativity is expected to remain an extraordinarily successful theory for macroscopic gravity, but it is understood to be incomplete. The future of gravitational physics will involve refining it, testing it in new regimes, and finding where it fails. This pursuit is not a rejection of Einstein, but a continuation of his project, deepening our understanding of spacetime. In the coming decades, humanity will watch black holes collide across the universe, image horizons with increasing clarity, measure time so precisely that altitude differences of centimeters matter, and use gravitational waves as a new form of astronomy. We will map the cosmic web with unprecedented detail, test dark energy with greater precision, and search for the universe's earliest signals. We may find hints of quantum gravity, detect primordial waves, or discover unexpected anomalies that reshape physics. Or the universe may continue to behave exactly as Einstein predicted, reaffirming the simplicity and elegance of general relativity. Whatever the outcome, gravity will remain central to our understanding of existence. It connects the smallest scales to the largest, the birth of the universe to its distant future, and the structure of spacetime to the passage of time itself. The future of gravitational physics is not merely a scientific endeavor, it is a journey into the deepest layers of reality. One of the most remarkable aspects of gravity is that, beyond being a physical interaction, it forces us to rethink fundamental concepts that humans once believed were obvious. What space is, what time means, what motion truly represents, and even what it means to exist in a universe governed by laws rather than by intuition. Physics has always challenged common sense, but gravity does so in a uniquely profound way. It transforms the very stage on which all of nature unfolds. The philosophical implications of gravity extend far beyond astronomy or mathematics. They confront questions about determinism, causality, perception, and the nature of reality itself. Gravity, in Einstein's conception, is not a force acting in a pre-existing space, but the curvature of spacetime created by mass and energy. This view dissolves the distinction between the world and its geometry. The universe is not something in space. Space and time are things the universe creates. This shift in perspective is not merely technical, it reshapes what it means to speak of place, motion, past and future. In everyday life, time feels like an absolute backdrop, a steady flow independent of what happens in the world. Yet gravity reveals this as an illusion. Time is not universal. It is affected by where you are and how fast you move. Two identical clocks at different heights tick at different rates because gravitational potential influences the unfolding of time. This is not a philosophical metaphor, but a physical fact confirmed with extraordinary precision. The philosophical consequence is that there is no single cosmic time that applies to all observers. Everyone moves through space-time along their own path, experiencing their own local time. Past, present, and future depend on motion and gravity, not on an absolute cosmic clock. This challenges long-held intuitions about simultaneity and raises profound questions about the nature of temporal reality. Philosophers and physicists alike debate whether time is something that flows or simply a dimension through which different observers trace different paths. Space undergoes an even more radical transformation. Before Einstein, space was assumed to be a fixed stage that exists independently of matter. But general relativity replaced this static structure with a dynamic one. Space bends, stretches, vibrates, and evolves based on the distribution of mass and energy. The shape of spacetime influences motion, and motion influences the shape of spacetime. This mutual relationship means the universe is self-shaping, not imposed on a static canvas. Human intuition imagines straight lines as the shortest paths, but in curved spacetime, these lines twist and bend through geometry that cannot be visualized in ordinary experience. The philosophical challenge is understanding that physical reality is not built from objects in space. Instead, space itself arises from the relational structure between events. This relational view echoes ideas discussed by philosophers for centuries, but general relativity gave it mathematical form. Gravity also forces reconsideration of causality. In Newton's era, causes and effects seem straightforward. Forces push or pull objects, and the effect propagates instantly across space. Einstein replaced this view with causal structure embedded in spacetime. Nothing travels faster than light, and information cannot propagate outside the light cone. Spacetime curvature modifies these cones, shaping what influences what. This structure determines which events can affect other events, redefining causality as geometry rather than mechanical action. Philosophically, this means reality is bounded by geometric constraints, not by forces acting at a distance. It also means the future is not completely independent of the past. The structure of spacetime constrains possible futures, shaping them from the moment mass and energy determine curvature. Another philosophical implication concerns the status of gravity as an emergent phenomenon. Some modern theories speculate, purely as hypotheses not yet proven, that spacetime itself might arise from deeper quantum or informational principles. According to these speculative frameworks, gravity might not be fundamental, but a manifestation of the collective behavior of microscopic degrees of freedom. While such ideas remain outside the scientific consensus, they highlight a philosophical shift: the possibility that reality is layered, with gravity arising from deeper laws. Even if these ideas turn out to be incorrect, the questions they raise about emergence, fundamentality, and the nature of physical law remain deeply philosophical. Black holes push these questions further. They are regions where spacetime curvature becomes so extreme that conventional ideas of inside and outside time and space break down. At the horizon, time slows relative to distant observers. Inside time and space swap roles. The singularity predicted by general relativity marks a place where spacetime ceases to behave as a manifold. Philosophically, black holes challenge the assumption that reality is smooth and continuous. They force us to confront the limits of understanding. What does it mean for a place to exist if no observer inside can communicate information outward? What does it mean for a region to have an end of time? These are not abstract questions, they arise from the equations governing the universe. The existence of black holes also raises questions about determinism. If information is lost in black hole evaporation, as Hawking once suggested, then the universe might be fundamentally non-deterministic. However, the dominant view today is that information must be preserved, though the mechanism remains unknown. This ongoing debate illustrates how gravitational physics intersects with deep philosophical questions about the nature of cause, effect, identity, and memory. Another profound implication arises from gravitational waves. These ripples in space-time demonstrate that the universe is not static but dynamic. Space can oscillate, stretch, and compress. When the first gravitational wave detection was announced, it was described as hearing the universe for the first time. Philosophically, this implies that reality is not merely a collection of objects, but a continuum capable of carrying vibrations and storing information over billions of light years. The fact that space-time can vibrate challenges the classical view that space is empty. Instead, it becomes a medium with properties, behavior, and structure. This invites questions about what space-time fundamentally is: a substance, a field, a geometric abstraction, or something emergent. Gravity also reshapes ideas about the universe's origin. The Big Bang marks not just the birth of matter, but the birth of time itself. Asking what happened before the Big Bang may be meaningless because before presupposes a temporal structure that did not exist. This challenges philosophical intuitions about cause and creation. If time itself emerged from an initial state, then the universe does not require a cause in the traditional sense. Physics reframes origins not as events occurring in time, but as transitions in the structure of spacetime. Gravity governs the universe's expansion, influencing its past and future. Whether the universe will expand forever or collapse depends on gravity's interplay with dark energy. This cosmic evolution challenges the philosophical notion of a static universe, which dominated human thought for centuries. Human identity is also reshaped by gravity. Our sense of up and down, balance, posture, and locomotion arise from Earth's gravity. Our physiology evolved under 1G, and our bones, muscles, and organs reflect this. In microgravity, the body weakens, fluids shift, and biological clocks adjust. Gravity shapes human perception, cognition, and even language. Concepts like grounded, falling, or centered draw metaphorical meaning from physical experience. Philosophically, this shows that human understanding is embodied. Our interpretation of reality is influenced by the gravitational environment in which we evolved. A species evolving in a different gravitational field would likely develop different metaphors, intuitions, and reasoning structures. Gravity also connects humans to the cosmos in a way that few forces do. Every person is composed of atoms forged in stars held together by gravity, planets formed in disks guided by gravity, and galaxies shaped by gravity. The iron in your blood came from stars that collapsed under their own weight. The calcium in your bones condensed in planetary systems created by gravity, collecting dust into worlds. Even the rhythm of the tides influenced early life on Earth. Recognizing this connection expands the concept of identity beyond individual bodies, locating each person within the cosmic network shaped by gravity over billions of years. Another philosophical aspect concerns the apparent fine-tuning of gravity. If gravity was slightly stronger, the universe might have collapsed too quickly for life to form. If it were weaker, stars and galaxies might not form at all. This sensitivity raises philosophical questions about why the universe has the parameters it does. Physics does not offer answers. These discussions belong to metaphysics rather than science. But gravity's role in enabling complexity makes the question unavoidable. Is the universe fine-tuned, or are there many universes with different gravitational constants? Multiverse theories remain speculative and outside consensus, but the philosophical implications of gravity's precision remain profound regardless of interpretation. The relational nature of gravity raises another philosophical issue: the meaning of motion. In Newtonian physics, motion requires reference to an absolute space. In general relativity, motion is defined relative to space-time curvature and other objects. There is no fixed background. This dissolves the concept of absolute rest. An object in freefall feels no force, it is following a natural path. Philosophically, this challenges intuitive notions of inertia, identity, and agency. Objects do not move through an independent space. They move within a geometric structure that responds to mass and energy. This viewpoint aligns with relational philosophies that argue reality arises from relationships rather than substances. Gravity also challenges the boundary between mathematics and reality. General relativity describes the universe with equations of extraordinary elegance. Space-time curvature, geodesics, and tensors form a mathematical language that appears to map directly onto physical behavior. This raises philosophical questions about why mathematics describes reality so effectively. Is mathematics discovered or invented? Does the universe follow mathematical laws because those laws describe deep structures of reality, or because mathematics mirrors the structure of the human mind? These questions extend beyond science, touching on epistemology and ontology. The structure of spacetime also affects the philosophical understanding of free will. In relativity, spacetime contains all events, past, present, and future, as part of a single, four-dimensional structure. This block universe interpretation suggests that the flow of time is a human perception, not a physical process. Events do not come into being, they simply exist at different coordinates in spacetime. Whether this interpretation is correct remains debated within physics and philosophy, but gravity, by shaping spacetime, directly influences these debates. If time is a dimension, not a flow, then the future may be as fixed as the past. This does not necessarily eliminate free will, but it reframes it as a pattern within spacetime, rather than a force that changes outcomes. Another consequence concerns knowledge and perception. Humans evolved to understand the world at low speeds and small scales. Gravity at astronomical scales operates in ways that defy intuition. Time dilation, space-time curvature, and gravitational waves lie outside everyday experience, yet they are real, measurable, and necessary for understanding reality. This gap between perception and reality raises philosophical questions about the limits of human cognition. How much of the universe can humans truly understand? Are there aspects of gravity or space-time that lie beyond comprehension? Or do mathematical models allow humans to extend understanding beyond intuition? Gravity reveals that human senses provide only a partial view of reality. The universe's true structure is stranger and more sophisticated than human intuition alone can capture. Gravity also reshapes the concept of nothingness. Empty space is not empty, it has geometry, curvature, and dynamic properties. Quantum fields permeate it. Virtual particles fluctuate within it. Dark energy influences its expansion. Gravitational waves ripple through it. This challenges philosophical ideas that treat nothingness as absence. In physics, nothing is something, a dynamic structure with laws and properties. This insight arises directly from the study of gravity and spacetime. Even the concept of location becomes philosophical. In curved spacetime, there is no unique way to define the distance between 2 points. The value depends on the path chosen. Parallel lines intersect or diverge depending on curvature. This challenges Euclidean intuitions that have shaped philosophy, art, architecture, and science for centuries. The universe does not obey the geometry that humans instinctively imagine. It obeys a deeper, flexible geometry shaped by energy and motion. Ultimately, gravity reveals that the universe is not static, simple, or intuitive. It is dynamic, interconnected, self-shaping, and governed by principles that defy common sense. This realization carries a philosophical lesson. Human intuition is not the measure of reality. Reality is the measure of intuition. Gravity invites humility, curiosity, and wonder. It reminds humans that the world they experience is only a tiny slice of a vast, profoundly structured cosmos. It challenges assumptions, expands perspectives, and offers a deeper understanding of existence. Gravity, from the moment humans first sensed its presence, has always felt like the simplest thing in the world. Something pulls you downward. Something keeps the moon in the sky. Something holds the planets in place. It feels so instinctive that it is easy to assume gravity is obvious, uncomplicated, and fully understood. But after traveling through centuries of scientific discovery, after peeling back layers of theory, observation, mathematics, and experiment, you now stand face to face with a realization completely opposite to that childhood intuition. Gravity is not simple. It is not obvious. It is not intuitive. It is not a force in the way people imagine. Instead, it is the quiet, omnipresent structure that shapes everything. From falling apples to colliding galaxies, From the ticking of atomic clocks to the birth of stars, from the passage of time to the evolution of the universe itself. And the more deeply you understand gravity, the more you see that everything you thought you knew was just the surface of something far stranger and far more beautiful. As you look back at the ideas explored so far, the first major revelation is that gravity is the curvature of space-time, not an invisible pull. This single shift in perspective reshapes everything. Instead of masses attracting each other across empty space, objects simply follow the straightest possible paths in a curved geometry. What you feel as weight is not gravity pulling you downward, but the ground pushing upward, resisting your natural geodesic. What you interpret as falling is simply free motion in curved space-time. This understanding removes gravity from the category of forces and places it as a fundamental expression of geometry. It exposes space and time as flexible, dynamic, and responsive, not static backgrounds, but active participants in the universe. Another key realization is that time itself is not universal. The flow of time depends on where you are and how fast you move. Clocks on satellites tick differently from clocks on Earth. Even raising your wrist a few centimeters changes the rate at which your watch experiences time. This isn't imagination or theory. It is a measurable fact built into technologies humanity relies on daily. Gravity does not merely bend space, it slows time. This forces a profound rethinking of what it means to age, to move, and to exist. Every person carries a slightly different timeline, shaped by motion, gravity, and location. The universe does not provide a master clock. Instead, it grants each observer their own unique progression through space-time. All of this leads naturally to the behavior of light and matter. Gravity does not act directly on light in the traditional sense. Light always follows straight paths. But because space-time is curved, straight lines appear bent. This distortion produces gravitational lensing, which allows astronomers to observe galaxies otherwise invisible. It distorts images, magnifies distant objects, and reveals the presence of dark matter. Gravity also stretches light, redshifting it as it climbs out of gravitational wells. Over cosmic distances, lensing becomes a tool for mapping the unseen skeleton of the universe. These effects confirm again and again that general relativity is not just a theory, it is the operating system of the cosmos. Perhaps the most dramatic expression of gravity comes from black holes. These objects demonstrate how space-time behaves when curvature becomes extreme. They hide their interiors behind horizons where escape velocity exceeds the speed of light. They distort time until the outside universe seems to accelerate infinitely relative to the infalling observer. They bend light into rings, twist magnetic fields, and launch jets that span entire galaxies. They merge, they echo, they ripple space-time, and through gravitational waves, they announce their presence across billions of light years. Black holes are not cosmic monsters swallowing everything in their path, as myths suggest. They are natural endpoints of gravitational collapse, expressions of geometry pushed to its limits. Their existence is confirmed not by speculation, but by direct observation, through shadows, accretion disks, X-rays, and gravitational waves. They stand as both triumphs of general relativity and signposts pointing to deeper physics, yet undiscovered. Yet despite its success, general relativity is not the final word. It breaks down at singularities where curvature becomes infinite and the laws of physics collapse. It fails to describe gravity at quantum scales. It cannot fully explain dark matter or dark energy. It does not merge smoothly with the probabilistic world of quantum mechanics. This does not diminish the theory, but highlights the frontier waiting ahead. Just as Newton's model was extended by Einstein, Einstein's model will one day be extended by a unified theory, one that describes gravity in terms of quantum behavior and reveals what spacetime is made of at its most fundamental level. Dark matter represents another frontier. There is overwhelming observational evidence for its gravitational effects. Galaxy rotation curves, lensing maps, cosmic structure formation, cluster collisions, but its nature remains unknown. Is it a particle, a modification of gravity, a relic from the early universe? The scientific consensus strongly favors dark matter as real, but its identity remains one of the greatest mysteries. It reminds us that the universe still hides mass and structure we cannot directly see, and it proves that gravity reveals truths long before other tools can. Dark energy expands the picture further. The acceleration of the universe is not predicted by Newton or Einstein's original equations. It is a discovery forced upon us by data. Something is driving the expansion faster and faster, pushing galaxies apart, while gravity tries to pull matter together. Whether dark energy is a constant property of spacetime, a dynamical field, or a sign that gravity changes over cosmic distances remains unknown. It forces the realization that gravity is not simply an attractive effect. It participates in the evolution of spacetime itself. Understanding dark energy means understanding the ultimate fate of the universe. The formation of large-scale structure shows gravity working over billions of years, sculpting filaments, clusters, voids, and the cosmic web. From tiny quantum fluctuations in the early universe, gravity amplified structure into the patterns we see today. The fact that such complexity arises from simple initial conditions illustrates the power of gravitational evolution. Structures form not because the universe is carefully arranged, but because gravity naturally enhances small irregularities. Over cosmic time, these grow into the architecture of galaxies, clusters, and superclusters. The universe's structure is not random. It is the cumulative imprint of gravity shaping matter across vast distances. Much of this story emphasizes that gravity is universal. One law governs everything. But universality does not imply simplicity. Gravity behaves differently on different scales, producing unique phenomena at each level. Tides on Earth, orbital resonances in the solar system, fusion in stars, degeneracy pressure in neutron stars, horizons in black holes, lensing in galaxy clusters, and acceleration in cosmology. The same equations generate all these outcomes, proving that a single underlying principle can yield wildly diverse expressions of nature. A recurring theme throughout this journey is the tension between scientific consensus and speculation. Science accepts only what can be measured, tested, or mathematically derived from validated theories. Everything else, wormholes, extra dimensions, emergent spacetime, multiverses, remains hypothetical. These ideas fuel imagination, but lack experimental evidence. It is crucial to distinguish between what is known, what is hypothesized, and what is purely conceptual. Gravity provides one of the clearest examples of how science progresses: cautious, rigorous, grounded in observation, skeptical of easy answers, and always willing to revise ideas in light of new measurements. But beyond science, gravity carries emotional and philosophical implications. It shows that humans do not live on a passive stage. They inhabit a dynamic space-time that bends, stretches, breathes, and evolves. Every step you take follows a geodesics. Every heartbeat unfolds in curved time. Every moment of your life is shaped by the structure of the universe. Understanding gravity means understanding the connection between the mundane and the cosmic. It reveals that human existence is not separate from the universe, but woven into its geometry. Gravity also inspires humility. The universe does not conform to human intuition. Time is not absolute, space is not flat. Light does not move in straight lines the way your mind imagines. Clocks disagree, Horizons hide regions forever. Waves ripple through spacetime itself. Stars collapse into objects where time ends. Galaxies collide and merge, while dark matter silently shapes their dance. None of this is obvious. Gravity teaches that the universe is not obliged to be simple, comfortable, or intuitive. It is as it is, and humans must expand their understanding to meet it. Yet gravity also inspires wonder. The fact that a human mind can grasp these truths, derive equations describing them, detect their signals with delicate instruments, and image their effects across billions of years speaks to something extraordinary about human curiosity. Gravity shows that the universe is complex but comprehensible. It challenges assumptions, overturns old ideas, and reveals deeper structure. It shows that knowledge grows not by clinging to familiar beliefs, but by questioning them. As this journey through gravity comes to an end, the most important realization is simple. Gravity is not merely a physical phenomenon. It is the story of the universe itself. It shapes planets, stars, galaxies, and time. It governs motion, structure, and destiny. It reveals the hidden framework of reality. It challenges humans to think beyond intuition and embrace a deeper, more accurate picture of nature. It connects the smallest moments of daily life to the grandest scales of existence. Understanding gravity is understanding the cosmos. And the more deeply you explore it, the more the universe opens itself to you, not as a place of random events, but as a coherent, ordered, evolving structure bound together by the curvature of space-time. You live within that curvature. You are shaped by it. You are part of it. And perhaps the most empowering truth is this: the universe is intelligible. You can understand it. You can study it. You can question it. You can continue where Newton, Einstein, and countless others left off. There are mysteries still waiting: dark matter, dark energy, quantum gravity, singularities, primordial waves. But these mysteries are not beyond human reach. They are invitations. Gravity has carried you from falling apples to curved space-time, from ticking clocks to merging black holes, from the earth beneath your feet to the cosmic web stretching across the universe. And the journey does not end here. This is only the beginning of what humanity will discover.